Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on inside as we jump into Chapter 3 of the Big Ideas Math Integrated Math 3 textbook on polynomial functions. Now this first section, 3.1, is on graphing polynomial functions. Then we're going to get into some other algebra stuff that will help us to graph polynomial functions again later near the very end of the chapter. And, you know, I am going to do something that I kind of swore I wouldn't do, which I got to do some graphs using tables, because this section here gets you to, it introduces you to polynomial functions, and I think probably in a very nice way. We got to use tables to just do the graphs for now and just go like, okay, I guess here's where the individual points go. And eventually we'll get into that table-less version of it after we learn all the other sections beforehand. Let me show you what I mean with this really fast. In this table of contents, we're going to start with this, the graphing. Then we got to combine like terms and do FOIL method and distribution and things like that. So some of the stuff you're going to go like, yeah, I know that stuff. There's some things in here you also won't know in section 3.2. 3.3, dividing polynomials. It's like using long division and things like that. It's quite interesting. We'll use remainders. Factoring, something you probably learned in IM3, and we're going to learn it with the bigger kinds of polynomials we're going to learn here. Solving polynomial equations, all based on the big complex ones, and the small ones you knew how to do. Zero product property, maybe some quadratic formula, maybe or maybe not. I have no idea. I haven't dived into it yet. Fundamental theorem of algebra sounds pretty important, all great, but it still kind of has an algebra basis to it. It's not until 3.7 that you actually get back into the appearance probably of some graphs, but in transformations you've seen that also as just take f of x and translate it 3 units to the right. So we might not do anything very specifically with it. It's just take this and do that with it instead of create your own. It's section 3.8. Section 3.8, analyzing graphs of polynomial functions. That's where you go back and do some of the ones again, but in a different light, in a way that, like, when I wouldn't graph using a table, this is how I would actually do those graphs. And section 3.1 is going to hit at those kinds of equations, but we're going to have to use graphs on 3.1, then get all that stuff that leads into it. And then 3.9 is going to be modeling. We'll see what we do there. Maybe some regression stuff, and I don't know, word problems, all that. So anyway, we're going to start with this 3.1 section. Normally I don't show you a table of contents, but I thought here it was really important to explain why we start with graphs and go back to graphs later. And hopefully that makes sense. So without further ado, guys, I'm going to go ahead and get started. If you want to jump to the description section down below, you can download the PDF thing of this, and as well as any graph paper I do provide for you guys. Follow the timestamps along with what you'd like to watch this video, for what reason you'd like to watch the video. I'm going to start with a lecture, then go to the 50 question problem set. Without further ado, let's go ahead and get started. We are going to identify polynomial functions and graph polynomial functions using tables, yes, and end behavior. I will use the tables, as they do. End behavior is a possibly new phrase for you guys. We'll get into it. Now, polynomial functions shouldn't be new to you. Almost everything, well, every quadratic we deal with is a polynomial, all that stuff. Recall that a monomial is a number, a variable, or the product of a number and one or more variables with whole number exponents. So, you know, 2x cubed and -3 and 4xy and, you know, things like these. These are monomials. When you put them together, this minus this plus this, you've created a polynomial, or any single one can be a polynomial. A polynomial is a monomial, or a sum of monomials put together. A polynomial function is a function of this form right here, and I don't want this form to over confuse you, but basically any of these a's are coefficients multiplied by your variables raised to powers. They're writing it in standard form as well. You can see that to the nth power is the leading term, and then they show an n minus 1 and stuff, all the way to a linear term and then a constant term. Now, any of these might possibly be 0, not the leading coefficient, of course, because otherwise it's not a polynomial of degree n, which they'll probably talk about. But it's the leading coefficient. Here we go. It's the leading coefficient. N is the degree of the polynomial. So if it's n is 2, it's a quadratic, and it can't be a quadratic if it's 0x squared. So there's that. Any of the other ones could be 0, so they could wipe out. Right? You don't need to have a constant term if it's 0. Anyway, that's why I'm saying don't get too stuck on this, but all of your exponents for your variables need to be whole numbers. 0 is a whole number, 1's a whole number, 2's a whole number, etc. They can't be negative, they can't be fractions, they can't be radicals, they can't be imaginary, you know, things like that. They need to be whole numbers. And a polynomial is in standard form when its terms are written in descending order of exponents from left to right. So the biggest exponent first, and downward. You're already familiar with some types of polynomial functions, such as linear and quadratic. Yep. Here's a summary of common types of polynomial functions. So a constant, and you've heard me say these phrases all the time, and I'll keep saying them. A constant, 1, has no x attached to it because x is to the 0 power, right? When they say degree 0, x to the 0 power is 1, that means it's gone. Negative 14, y equals negative 14 is an example of that. Here's a linear one, 5x minus 7. You think graphing a line. Here's a quadratic. This becomes a parabola. We now know how to graph things like that, even at a standard form, using negative b over 2a, yada, yada. But we're going to start graphing these ones. We're going to start graphing cubics and quartics and things like that. Now keep in mind 2 is quadratic, whereas 2 is quadratic, whereas 4 is quartic. There's a difference there, but we're going to be able to graph these two. Now we're going to use tables for them this time, but we're going to understand the nature of these graphs, of these polynomials as well. First, we're going to identify polynomial functions. Decide whether each function is a polynomial function. If so, write it in standard form and state its degree, type in leading coefficient. Sounds like a lot of stuff you've done in IM2, and so hopefully this can go pretty quickly, even in lecture portion. Part A, it's definitely a polynomial. Actually, all these are no, they're not. Part A is a polynomial. These all have whole number exponents. This is degree 3, degree 1, degree 0. So all whole number exponents. And it's already written in standard form, as they say, because it's in descending order of degree of 3, 1, and 0. It doesn't matter what the coefficients are as far as what's negative, which one's bigger and stuff. The order is based on degree. So this is a cubic. It's a cubic because it's of degree 3. That's what they're saying. Degree 3 is a cubic. It has a leading coefficient of negative 2. And remember, the leading coefficient is determined once it's written in standard form. B, part B, is also a polynomial. We have degree 3, 4, and 0. It doesn't matter that this coefficient is irrational. That's okay, as long as these are whole numbers, the exponents for the variables. And written in standard form, you need the degree 4 term to be first, right? Degree 4, and then degree 3, and then degree 0. So they wrote that as the following: root 2 x to the 4th, da, da, da. It is a degree 4, so it's a quartic polynomial. And its leading coefficient is root 2. Now, you might wonder, what does the leading coefficient matter? Why is it so important? It is for the graphing. Most so because of its sign. Square root of 2 is positive. Because it's positive, that's important. This negative 2, it's negative. That will dictate things about it. You already know that with, like, when a is negative, it's upside down. That's kind of the thing that will be important about it. That's the most important aspect. Not just stretch factor, but also which way it goes. Anyway, I just wanted to tease that. C is not a polynomial, and that's because it's x to the negative first power. And also, if you know, negative first power also means, it's like 7 over x, like that. So this is part of a rational set, rational functions, not a polynomial. So we don't, you can try and write it in standard form and stuff, but it doesn't have a name like quadratic or anything like that. It's no longer a polynomial. And so we probably don't identify. It says if it's a polynomial, write in standard form, da, da, da. So we say it's not in this case. Okay. And this one right here, also not a polynomial. This 3 to the x power, x is not a whole number. X could be a whole number, 0, 1, and 2, but it could also be negative 1 and 0.1 and things like that. So not a polynomial. This is an exponential function with a combination of some quadratic behavior, but also not a polynomial. Okay, so I went kind of slowly through that to describe everything, but yeah, we'll keep going. Evaluate a polynomial function. Probably one of the easier things you can do, but we need to know how to do it. Make sure you know your order of operations, because this is how we're going to be graphing right now. We're going to use a table. So evaluate f of x equals this function, and it's polynomial, by the way. There's no question about it. They'll make it one. When x equals 3. That means take f of 3. Substitute 3 for x, and figure out what you get. Now, you don't do 2 times 3 first. You do 3 to the 4th first. 3 to the 4th is 81 times 2 is 162. You see 2 times 3 is 6. 6 to the 4th, I believe, is 1296. 1296 and 162 aren't the same number. So you can't just go whichever order you want. And by the way, you can type these in the calculator if you'd like as well. Let the calculator do your order of operations for you. Anyway, 3 squared is 9 times 8 is 72. So we subtract that. 5 times 3 is 15. And minus 7, you get 98. So f of 3 is 98. That means when x equals 3, y equals 98. That means 3 comma 98 is a point that's on your graph if we graph this. The end behavior of a function's graph is the behavior of the graph as x approaches positive infinity or negative infinity. This seems like its own section. Okay, this seems like its own section, so I'm going to go here. So the end behavior says, as we go forever to the right, how's the graph behaving? Because a lot of our graphs, they seem to go forever up in the end or forever down in the end, and we're expecting the same thing here on polynomials. So as we go forever to the right, eventually, what's the graph's long-term end behavior? Is it finishing forever up or forever down? Going to positive infinity or negative infinity? And that stuff, again, matters for me when it comes to my tableless graphing stuff and what we get to say with it over time. As it goes forever to the left, is it going forever up or forever down? We're going to start recognizing behaviors of polynomials based on the degree of the polynomial, whether it's even or odd, whether the leading coefficient is positive or negative. And that's what they're saying here. For the graph of a polynomial function, the end behavior is determined by the function's degree and the sign of its leading coefficient. So, when you have an odd degree polynomial, and I know we haven't done cubics really yet before. We've done linear ones, which are also odd degree. Odd degree means the degree of the polynomial is odd, to the first power, to the third power, to the fifth power, to the seventh power, etc. When it's an odd degree, what you'll have is opposite end behavior on either side of your polynomial. So if we go to the right and we go up here, we're going to go to the left and go down here. So it's that opposite effect. You know, linear functions do the same thing. I'll go up and to the right and down and to the left, or I might go down and to the right and up and to the left. Okay? Whereas an even polynomial, an even degree polynomial, such as to the second power, a parabola, will start and finish in the same direction. It'll either start up, finish up, or start down and finish down. Now, it's not just for x squareds. It's also for ones to the fourth power and sixth power, eighth power, 10th power, etc. All of those are even degree polynomials, and they start and finish in the same direction. Now, the reason why is because when you raise something to an even power, it'll turn positive no matter whether the number was positive or negative. 4 to the sixth power and negative 4 to the sixth power, don't ask me what the number is, but they're big positive numbers. That's why they both start and finish upward. Now, when the leading coefficient's negative, it's going to flip over, like this. Let me move myself. I realize I'm covering this up. Whereas when you have an odd degree one, what happens when I do 4 to the fifth power? Well, that's a big positive number. What's negative 4 to the fifth power? That's actually a big negative number because you multiplied 5 negatives together, so it finishes negative. So they have an opposite effect of each other. When one version of the number is positive, the other version is negative. And keep in mind, we're talking about end behavior. As x approaches positive infinity, f of x approaches positive infinity. As we go forever right, we're finishing forever up. As we go forever left, we're finishing forever down. That's that as x approaches negative infinity, f of x approaches negative infinity. Okay? Now, we're talking end behavior, not mid behavior. Notice how in the middle it does this. Oh, we're going down. That must be the... Nope, it's going to go back up. There are some things that higher degree polynomials will tend to do in the middle. They have more complexity. They have the ability to turn and go back and stuff. And the higher the degree is, the more likelihood that there are some turns in the graph. They reach relative maxes and mins. They hit the x-axis multiple times here and get different intercepts. Those are more possible as you get to higher degree polynomials. This could be a cubic or a quintic, fifth power, things like that. Anyway, with a positive leading coefficient, I'll say something like it starts down and finishes up. For an odd degree, you'll hear me say that phrasing. That's probably not the way I'd say it correctly, but when I say starts down, I mean it comes from the bottom. I'll say starting from the bottom, now we're here. It starts down and finishes up. Negative leading coefficient for an odd degree, it starts up, finishes down. A positive leading coefficient for an even degree, sorry if I said even degree before, I meant odd. For an even degree positive, it starts up, finishes up, even though it might have some turns in between. And then an even degree negative leading coefficient, it starts down, finishes down. That's going to be my phrasing, but this is how we're going to have to write them. You'll see me write it possibly a little slightly altered because of habitual reasons, but there it is. All right, let's take a look at an example. Describe the end behavior of the graph of f of x equals this polynomial here. First, let's identify the fact this polynomial is in standard form. I'm going to assume they're going to be writing in standard form for us. If not, we have to rewrite in standard form. Why is standard form important? Because of the degree and the leading coefficient. The degree matters based on the fact that it is even, and the leading coefficient matters because of the fact that it is negative. When you have an even degree polynomial with a negative leading coefficient, we are going to have the trend of starting down and finishing down. It's going to come from the bottom. It's It's going to do some stuff going through, and it's going to finish at the bottom as well. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. Both of those things we're going to write, and they write them right here. Boom, boom, boom. I kind of do it the other way. I tend to write this. I say, as x approaches positive infinity, what's y doing? Boom. Because it's kind of like cause and effect. As we plug in x, here's what y does. So in this case, as x approaches positive infinity, y approaches negative infinity. And then I'd probably write on another line, as x approaches negative infinity, y also approaches negative infinity. If they do the, it doesn't matter which order you really do it, as long as you write the as with kind of with the x, right? That's the hypothesis that we're meeting, or the condition that we're meeting, I should say. And as long as you have it in the right order. I say positive infinity here, that's got to be negative infinity, etc. And here's the actual graph according to a graphing calculator. So it does have some turns along the way. However, the end behavior is it starts down and finishes down. Okay, graphing polynomial functions. Here's where we are actually going to use a table. To graph a polynomial function, first plot its points to determine the shape of the graph's middle portion. So they want you to first plot some points, figure out what's going on. This is where our use of a table will happen. This is where I'm like, I guess they are going to have us go from -2 to 2, -2 to 2. I'm going to do the same thing, I suppose. We'll get some of the points and understand how this thing kind of hits some curves, okay? So we're going to graph part A, f of x equals -x cubed plus x squared plus 3x minus 3, a cubic function. That's an odd degree. It's got a negative leading coefficient. We understand an odd degree with a negative leading coefficient should start up and finish down, something like that. So that's the expectation of our polynomial. So we're going to plot some points, plug in -2 for x, -1, 0, 1, and 2, do the order of operations that we would do before, be very careful on them. Apparently these are the numbers we get out, so these are the points that we plot. -2, 3, -1, -4, 0, -3, 1, 0, and 2, -1. And you get just those points there. Obviously they already have the graph, so we try and makeshift what happens in between, and you might not necessarily know, and I might not necessarily know. How would I know whether the graph actually hits this peak before going back down, meaning hitting another x-intercept, versus actually just hitting this and going back down? I won't actually know. You know what I mean? I won't actually, unless I plot the points in between. There are other ways you could figure some of those things out, but we're not doing that till like section 3.7 or 3.8 or whatever it is. Anyway, we're going to plot some points. We're going to use a table. The degree is odd and the leading coefficient's negative, so we know that it's also going to have this, oh look, maybe we can place this right over. It's also going to have that appearance and take it on, so we're going to use the end behavior to connect the rest of the graph and get that. I don't know if we're supposed to write all the end behavior stuff. I didn't see it ask us to do that, but the second question has a positive x to the fourth, and then we're going to plug some things in, so use the table, go from -2 to 2, get your points, plot them. And the end behavior of this one, see, you can see there's some middle behavior that's going to be significantly different from end behavior. It's a positive even leading coefficient. So it's going to start, positive leading coefficient, even degree polynomial. So it's going to start up, finish up. But how specifically is, I guess, based on the individual points. So we get some of these points, try and connect them and make sure the end behavior is aligned. And I guess that's the goal when we do those graphs together. All right, sketching a graph possibly in a generic way. Generic way meaning maybe not getting every bit of information, but a lot of it. And we're going to talk about increases and decreases and stuff like that. That's going to be a huge part of what we do. Sketch a graph of the polynomial function f having these characteristics. The function is increasing when x is less than 0 and greater than 4. So here's x equals 0. So less than 0, we're seeing the increase. That means to the left of 0, all the way up until 0, we see an increase. So it's going up that entire time. It's kind of tough because the graph's already drawn for us that I can't really do it with you. Here's when x equals 4. So greater than 4, we also see that increase. You can see where it hits the bottom and goes there. It's decreasing between 0 and 4 right here. So it's going up until we hit x equals 4. It decreases, or 0. It decreases after x equals 0 until it hits 4. And then it increases the rest of the way. That's the nature of that. So we know the end behavior. It's greater, the y's are greater than 0 when x is between -2 and 3. This is a nice kind of like puzzle to figure some things out as far as when it's positive, when it's negative. And these are things we might have to describe for ourselves later. But now we have a positive zone, right? We have a zone when we're above the x-axis, and that is right, I'm trying to give you a fill, between -2 and 3, it's above the x-axis. That doesn't state that it can't be increasing in some parts, decreasing in other parts. Absolutely it can, but it's positive there. It's also positive when x is greater than 5. It's kind of telling you what your x-intercepts are. At -2 and 3, we have x-intercepts because it stays increasing until then. That must mean it has to hit 0. And then greater than 5, it's increasing as well. And then it's decreasing on the, not decreasing, it's negative, it's negative when we are less than -2, so we're negative there. And then between 3 and 5, we're also negative, so we're underneath. You can see it on those ones. So we try and do those, and we can describe the degree and leading coefficient based off this thing here. The degree should be odd because it has alternating starts and finishes. Okay, it's an odd degree. And the leading coefficient should be positive because it starts down and finishes up. That's the nature of odd degree ones. And they have that written right down here. Degree is odd, leading coefficient is positive. Okay. Example 6, solving a real-life problem. Electric vehicles, a real-life problem. Sorry. The estimated number, V, in thousands of electric vehicles in use in the United States can be modeled by this crazy polynomial function. I hope we can use a calculator for that. Where t represents the year, with t equals 1 corresponding to 2001. So t equals 0 corresponds to 2000. Use a graphing calculator to graph the function for the interval 1 to 10, although t equals 0 doesn't seem to apply. Maybe electric vehicles weren't around in 2000. But for the interval 1 to 10 for this polynomial. So we're not looking at the entire end behavior from, negative infinity year to positive infinity year. We're just going from the years 2001 to 2010, right? So we might not see the entirety of this cubic doing everything, but describe the behavior of the graph on this interval. Well, we got to use the graphing calculator for that. So they use the graphing calculator. They set a window range from 0 to 10, just like that, which is good. And they find some snapshots of where the curve is actually described. So describe the behavior of the graph this interval. To me, it seems to increase for a while up until about year 2005 or 2006 or so. And then it kind of stalls out. I guess people were buying into the craze of electric vehicles, and then everyone's kind of bought one at some point. They're kind of in use at that point. That's my description anyway. Let's see what they say. From 2001 to 2004, number of electric vehicles in use increased. Around 2005, the growth in numbers is slowed and starts to level off. Then the numbers, start to increase again. Yeah, from 2009 to 2010. So that's their description. So we're going to have to do the same kind of stuff later. What was the average rate of change in the number of vehicles in use from 2001 to 2010? Guys, this is where you're doing a slope. What's the slope from here to there, right? You're trying to find just the rise over run. So you have to figure out what what was it? V of 1 is, I guess not V of 0, right? V of 1. You have to figure out why did they go from 0 to 10 if we got to go from 1 to 10? So here's 2001, I guess. So you got to go from V of 1. I'm trying to mark it, sorry. From V of 1. Oh, I take it back. That 0 is for the y. This is for the x. So V of 1 to V of 10 is right there. So what is V of 1? What is V of 10? I don't know. You got to plug it in. But there are those numbers. Find the difference between those two, right? How many electric vehicles, in thousands, I think they said. 58,000 minus 18,000. Divided by 9 years that have passed. So an average of 4.4 thousand electric vehicles are purchased per year. The average rate of change. Part C, do you think this model can be used for years before 2001 or after 2010? It's possible. It just depends on when they were made and stuff like that. But at some point, the end behavior is going to take over and say there were negative vehicles in place and there's an infinite number. There are hundreds of thousands of stuff. So maybe not so much. Maybe the model breaks. I'm going to say that it's possible, but not for very long after. You really have to see this gradient flux. Probably not. Because the degree is odd and the leading coefficient is positive, v of t goes negative as t is negative, v of t is positive infinity as t goes to positive infinity. The end behavior indicates the model has unlimited growth as t increases, which wouldn't be the case. While the model may be valid for a few years, that's what I was saying, after 2010, in the long run, unlimited growth is not reasonable. Notice in 2000 that v of 0, oh look, already in the year 2000, it's already negative, and the model already breaks for that part. Because negative values of v of t do not make sense given the context, you can't have negative electric vehicles in use, the model should not be used for years before 2001. Totally reasonable, totally makes sense for this stuff. All right, guys, before we start with this stuff, I'm going to have to quickly pause, and then I'll get right back to it. Okay. Okay, here we go. All right, let's get to the vocabulary and core concept check. Number 1, explain what is meant by the end behavior of a polynomial function. It explains what are your y values doing as x goes forever right and goes forever left. What are your y values doing of your graph as you increase infinitely in the left and right directions? That's kind of my layman's terms version of it. Right? As we go forever left, what are your y values doing? As we go forever right, what are your y values doing? Now, when I say all that, we only see that as forever going up or forever going down. There are some graphs where it'll approach a constant number and things like that. We're not doing those for polynomials, but there are other graphs that will do it, and we'll probably talk about them. Exponential functions actually have that when it approaches the asymptote, things like that. Which one doesn't belong? Which function does not belong with the other 3? Explain your reasoning. I'm guessing one of these is not a polynomial, and I see which one is not. So what I'm looking for, really, it's my first hunt among them. If this is A is a polynomial. It's also in standard form, degree 5, 2, and -2, and a positive leading coefficient. Keep all that in mind. This one also it's not in standard form, but it is a polynomial. That constant is fine. It's next to the 0 power. It's degree 3, 8, and 0. Again, not in standard form, but still a polynomial. You'll see one that actually breaks, and it's right here. This is different. This negative first power, this is not a monomial term, even though these are, but altogether, that means this is not a polynomial as a whole. So that one is, well, not. And then this one is also a polynomial. This is degree 1, degree 4, and degree 0. Even though these two, I guess you can't really combine them, whatever, but they are of the same degree. So this one here, not a polynomial. And again, it's not a polynomial because that -1 there. Whole numbers, see, you might say, Mr. Robinson, why isn't -1 a whole number when 1 is a whole number? They're both integers. Whole numbers start with the number 0, and that number 0 matters because constants need to be able to have that, right? X to the 0 power. So to be a polynomial, it needs a whole number exponent, 0, 1, 2, 3, etc. All right, guys, we're going to get to the core problem set. Numbers 3 through 50 are coming up here. Let's go ahead and get started on it. Actually, give me one more second. I have to fix one more thing. Okay. All right, let's go ahead and get started. Okay. I just didn't have all my windows popped up, basically. What's the problem? All right, in exercises 3 through 8, decide whether the function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. So once again, if it's not a polynomial function, we won't do any of those things. So number 3 is f of x equals -3x plus 5x cubed minus 6x squared plus 2. Totally a polynomial. All the terms are monomials. Polynomial. Totally. All of them are monomials. They all have variables with whole number exponents. Remember, 2 also means 2x to the 0 power. I'm not going to say that very often, but I wanted to state it there. That being said, this is degree 1, 3, 2, and 0. In writing in standard form, the degree 3 term is going to be first, and then the degree 2 term, and then the degree 1 term, and then the degree 0 term, like so. So there's standard form. Standard form. State its degree, type, and leading coefficient. All of these things are now based off the leading term in standard form. That's why we also wanted to write in standard form. So the degree is 3. The type, that makes it a cubic. I don't believe we're referring to, because it doesn't matter for us when it comes to graphing, but we're not calling it a quadrinomial, 4 terms or whatever. We're just talking about degree 3 makes it a cubic. And then leading coefficient is 5, which, again, what matters for us is that this is odd and that this is positive when it comes to us graphing it, or determining end behavior at least. Number 4, P of x. P of x equals 1/2 x squared plus 3x minus 4x cubed plus 6x to the 4th minus 1. 5 terms in total. All of them have, let me write the degrees up top as I kind of did last time and see if it fits for you. Degree 2, degree 1, degree 3, degree 4, degree 0. Because of all of that, it's a polynomial, so we're all good there. As far as standard form goes, we got to rearrange these things. So standard form, let's bring it about. We are going to get the degree 4 term first, highest one. So negative, oh, sorry, I was looking at the wrong one. 6x to the 4th, and then minus 4x cubed plus 1/2 x squared plus 3x minus 1. There's your standard form. This has a degree of 4. That is known as a quartic. I don't know how high we're going to go on degrees. It looks like they're not really, if they're not calling the other ones what they are, then whatever. But type makes it a quartic, not quadratic. And the leading coefficient is that positive 6, yo. All right. Now, what I'm realizing, I'm going to start copying down number 5. And what I'm realizing on this is it's been a while since, you know, not a while since I made IM2 videos, but, you know, since I made fall semester IM2 videos. And IM2 videos in the fall semester were a lot of algebra things. It's been a while since and I only just started, since I've been copying down problems with a lot of terms and things like that. IM2 didn't have quite as many, so it's going to be a lot of writing on my end. You know, I got to copy all these things down, and I'm going like, oh yeah, that's what it feels like. Anyway, this is degree 4, 3, and 1, and this one's negative 2. This is a big This one makes it not a polynomial when you have that. And if it's not a polynomial, then we shan't express anything further when it comes to standard form, degree, anything like that. It's just not a polynomial, and we'll leave it. So we're done on number 5. I'll take more of those, please. Little less writing, huh? Number 6. Number 6, g of x equals root 3. Now, root 3 is fine, right? It's just the constant term. It can be irrational as it wants to be. Plus minus 12x plus 13x squared. This is degrees 0 and 1 and 2. Totally a polynomial. However, its standard formness leaves a lot to be desired. Indeed, we're going to have to rewrite this in complete opposite order. G of x equals 13x squared minus 12x plus root 3. It's a quadratic. It's a degree 2, and the type is a quadratic. Don't forget those ones, right? Don't forget the ones you should already know. You know what I mean? Leading coefficient is 13. Positive 13. Okay, number 7. This time I'm not going to write the numbers on top. Let's see if we can determine everything with it. I'll say them out loud. But here we go. We got degree 2, degree 4, degree 3, degree 0, degree 1. All whole numbers, yes? That makes a polynomial. Now let's find the largest one. Degree 4 was the largest. So let's go ahead and rewrite that standard form version. We'll have degree 4, degree 3, degree 2, degree 1, degree 0. Yeah, they really get big into the whole, we're going to make irrationals, we're going to make fractions, we're going to make it look really different and confuse you into whether something is a polynomial or not. Just look at the degrees of the exponent, or whether the whole numbers and stuff. Anyway, degree 4 again, so it's going to be once again a quartic. However, that root 7 over here is negative, which is going to be a different kind of quartic if we came to graphing it, but negative root 7. And finally, number 8. All right, here we go. H of x equals degree 4, degree 1. We'll talk about this degree, but that one stands out a little bit differently, right? This is degree 3 and degree 0. Now, this one, I made mention of it in the lecture that you can turn this into something else. Remember, this term could also be rewritten as negative 5x to the negative first power. Because of this, this is a no-go. Not a polynomial. This is degree negative 1. That's what it is. It's degree negative 1. So this is not a polynomial. That part is rational that way, and it breaks what it does that polynomials do. So that one's it. We're going to leave it at that. Okay. All right. Let's go to numbers 9 and 10 on error analysis. In exercises 9 and 10, describe and correct the error in analyzing the function. All right. This one here, f of x equals da da da. F is a polynomial function. The degree is 3, and f is a cubic function. The leading coefficient is 8. I agree on it being a polynomial. We have degrees 3, 4, 1, 2, and 0. The problem is everything here. Everything here is a problem because they're treating this as the leading term. Remember, the leading term isn't the one that's written first. It's the one that's written first when it's in standard form. So 8x cubed is not the leading term. Although this is a let me get a bigger text here. Although this is a polynomial function, they outright stated the first term as the leading term, but neglected to rewrite it in standard form. Everything else afterward is incorrect. So let's correct it. I'm not going to recopy the problem, but what I'm going to do is rewrite that problem in standard form. And then we'll go ahead and address all the things. Now, what they did is correct based on if that was the leading term. But it's not. So, what is the actual leading term? Well, find the highest degree term. Now, that was me stating all that knowing that it wasn't the highest degree term. This is degree 3. This one's degree 4. That's the highest. So, degree 4, we got to say negative, and that can answer all the questions after that. But negative 7x to the 4th, and then everything else, right? Degree 3, degree 2, degree 1, degree 0. And by the way, I don't know if we've done it yet or not. I feel like we have. You can, I'm not going to say skip degrees, but you can be missing a cubic term in a quartic, right? It can look like that. It's possible. Not in this one, but you don't have to have every degree on the way down. So degree 4, 3, 2, 1, 0 is not always the case. Anyway, what do we need? We need the degree. So the degree is 4. It is a quartic, that is its type. And the leading coefficient here is negative 7. So those are the fixes for this one. It is a polynomial. They were totally right on that. I'm not addressing that part. I'm only correcting the mistakes. And that would be the mistake on number 9. Number 10. F of x equals 2x to the 4th plus 4x minus 9 root x plus 3x squared minus 8. F is a polynomial function. The degree is 4. F is a quartic function. Leading coefficient is 2. Well, I'll tell you what. Although they didn't rewrite it in standard form, this would still have been the leading term because 4 is the highest value among these, 4 and 1 and 2 and 0, and we'll talk about this one in a second. But this still would have been the highest, therefore it would have been a quartic, and this would have been a leading coefficient. Here's the problem. They said it's a polynomial function, but it's not. On number 10, there's a term that's breaking it, and you can tell which one it is, I'm sure. It's this guy right here, and I'll explain why. Now this time they have everything else correct. If this was a polynomial function, their leading term info would have been correct. However, this is not a polynomial function because one of the terms is not a monomial. Let's see. Let me write it. Negative 9 root x is not a monomial. The degree of this term is, does anyone know? What you want to do is think about what power do you raise your variable to make something a square root. Same thing with, remember when this thing was in the denominator, right here, you go like, oh, this is to the first power, it's all good. No, when it's written in the numerator and such, it's x to the negative first power, right? So that one's not a whole number exponent. What's the square root of x's exponent? That's x to the 1/2 power. The degree of this term is 1/2. 1/2 is not a whole number. So the answer to this thing is f is not a polynomial function. So that's the correction. This is not a polynomial function. That's my correction. Oopsie. Now, this, yes, negative 9 root x is the same as negative 9x the 1/2 power. Therefore, doesn't work. Not a whole number. Okay. In exercises 11 to 16, evaluate the function for the given value of x. So guys, this is just straight substitution of things. And in fact, this might help us later. If I do these ones slowly, then when we do graphs of ones later, maybe I don't have to do as much in the substitution aspects. I could maybe even use a graphing calculator. I don't know if they'd really want us to or not. But these ones, we'll go slowly through them as far as substituting values in. So let's just write exactly what's written to begin with, copy down the problem. And then, oh, and by the way, I'm imagining, I'm going to look at them right now. Yeah. So obviously, well, listen, they'll first of all be polynomial functions. You're good there. But also, they're going to write them in standard form. At this point, they're going to treat you with some respect and go, okay, now that you know what standard form is and blah, 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 we're going to give it to you in standard form. And that's not your objective. Your objective is to now do evaluations. So x is -2. We're going to substitute -2 for x as follows. And like I said, I'll go slowly through these problems completely. As far as bit by bit. So we're substituting -2. Now, like I said in the lecture, order of operations matters here. We start with -2 to the 4th. Then we multiply by -3. We don't do -3 times -2 and then raise it to the 4th. That's a different answer. -2 to the 4th is 16. Positive 16, by the way. -3 times 16 is -48. And that's important that I'm stating that positive. Remember the whole even degree functions, they would have got it either starts up, stays up, or starts down, stays down. That's because you raise something to an even power, it turns positive. Now times negative means it's going to turn negative, but so what if 2 to the 4th times -3? Anyway, -2 cubed is -8, times 2 is -16. -12 times -2 is positive 24, and then we got a -6. We got a -6, people. -48 minus 16 is -64, plus 24 is -40, minus 6 is -46. H of -2 is -46. That is us evaluating the function. To remind you what this means, and not that it matters for these problems, but it will for graphing, what it means is there's a point on your graph that's -2, -46. Okay, that is its meaning. That's what we did. Substitution of one value in x to get a y. Okay, number 12. Now we're going to substitute -7 for x. They really want to get into the practice of substituting in some negatives and using your order of operations along the way. All right, we got a quadratic function here, folks. X equals -7. Let's do f of -7. Calculator, get ready. I don't actually know that one. I can start to think about it as I'm writing this down. I don't know it. Okay. Now, I'm still just going to do one at a time. Obviously, I could let my calculator do the whole thing, but I'm not going to. I just want to figure out 7 to the 4th power. Well, it's going to do times another 7 after that. But yeah, 7 times 7, -7 to the 4th power. -7 to the 4th power is some number times 7 is 16,807. -7 squared is 49. Times 10 is 490. We're going to subtract 490. I'm going to use my calculator for this as well. 14 times -7 is -98. And then minus 26. All right, calculator. Help me out, please. 490 minus 98 minus 26. I expected I was going to do this without a calculator, and I didn't realize how big or small the numbers would get. Hey, it's still in the 16,000s. And this would be a point we'd plot on the graph as well, but it's quite high up. I don't expect we're going to do something that large. Okay, number 13. G of x. By the way, there's reason, when I'm thinking about some future sections we're going to be doing, there's reason we need to do substitution of values into these things. Generally, what we do it for is to test and see if we can make something equal 0. You'll see what I mean in the future when we actually play with that. But in general, I try and not graph these kinds of functions without with a table. But today we will. All right, g of 8. G of 8 is 8 to the 6th power. Once again, a number I do not know. I want to think about that one, though. Minus 64 times, yeah. I don't know if this is meant to say just use the calculator straight up. But guys, these are pretty big numbers. These ones are all right. So let's see. When I'm thinking of 8 to the 6th, oh, that's just going to be too big. I won't know that. I won't even bother. All right, 262,144 minus, I think this is the same number twice, because 64 is 8 squared times 8 to the 4th. I think we're going to get minus 262,144. This might be one where it's like, who cares? Let me triple check that I know what I'm talking about. 8 to the 4th. Yes, it is. Who cares what these numbers are? They cancel each other out. Remember, 64 is 8 squared. 8 squared times 8 to the 4th is 8 to the 6th. Anyway, plus, so maybe we were supposed to do this one without a calculator. So these are gone. So 64 minus 56 is 8. 8 minus 51 is negative 43. Wait, did I say that right? I think so. Negative 43. Where did my 8 go? 8, right there. All right. 8 minus 51 is negative 43. Okay. Number 14. And if I calculated that wrong, just obviously fix that for yourself. You get the idea, hopefully, in what we are doing. G of x equals negative x cubed. Careful with that. Plus 3x squared plus 5x plus 1. And we're going to substitute negative 12. Now, be careful on the first one. Notice what I'm doing for substitution each time, guys. I am not skipping steps for your sake. I want to make sure you understand. Negative, the opposite of negative 12 cubed. Although this is a cubic, so it's going to cancel it out anyway, do not take these and say opposite of a negative is a positive. You first got to cube the negative and then apply the negative there. So just please, please, please be careful. Again, it's best that you just use parentheses around your substitution. It goes straight in for x, wherever your x is, and then you evaluate off of that. G of negative 12. All right. 12 cubed. Man, I forget these numbers. That's a problem. For me, not for you. 1728. Maybe I didn't know that one. So remember, negative 12 cubed is negative 1728. Opposite of that is positive. 12 squared is 144 times 3 is 432. Minus 60 plus 1. Can I do it without a calculator? Here we go. 2160. I think so. Minus 60 plus 1. How about this? Minus 59. 2101. The main reason I showed that was not because it was easier for me to do. It's actually easier to do 2160 minus 60 and then plus 1. I want to show you that if you do things in like a different order where you're like, oh, combine these and then combine these, that's fine. Just don't do 60 plus 1. Don't say minus 61. No, it's negative 60 plus 1. That's still negative 59. So I wanted to show that and go like, if you do combine some things, make sure you treat the signs as what they are, right? Just be very, very, very careful. Some things can really, mess up if you don't do anything right with that. All right, let's go to number 15. P of x. By the way, when we do our table stuff, we're probably just going to go from negative 2 to 2. That's what they did in the lecture stuff as well. So these bigger numbers, or this fraction, for example, are probably not ones we'll be bothered by. But these, again, are things we got to know how to do. All right, I'm going to go completely calculator free, provided that, meaning I'm going to go with fractions. I know most of the decimals on these things, but I'm going to go fraction based on this one. Meaning common denominator, all that. I'll turn it into a decimal at the end if it's a clean one that I'll know, or if it's exact. So this is 2 times 1/8 plus 4 times 1/4 plus, I'll leave the 6 times 1/2 here one more time just to get it brewing. All right, 2 times 1/8 is 2/8, which is 1/4. Plus 4 times 1/4 is 1, plus 6 times 1/2 is 3, plus 7. So you have, now I can see where some people would go with this. I thought there'd be more fractions. 1/4 plus 11. A lot of people are going to write 11 1/4. I guess. We don't really do that, though. We have two options here. I'll accept 11.25. All right, that's fine. Otherwise, you can say 44/4, right, which is 45/4. So improper fractions or exact decimal. We're not doing mixed numbers here, y'all. Even though, listen, the mixed number probably makes more sense than the improper fraction when it comes to graphing it. How are you going to graph 45 fourths? I don't know. How are you going to graph 11 and a quarter? You go here. I get it. We just don't say that anymore. I don't know why. We just don't. I do know why. I'm just not going to be expressive about it. 5x cubed minus 3x squared plus 2x plus 4. Basically, don't expect that on an answer key. All right. Negative 1/3. Okay. They're going there. 5 times negative 1/3 cubed minus 3 times negative 1/3 squared plus 2 times negative 1/3 plus 4. I think this time it's inevitable that we're going to have to deal with some fractions. We'll see what they do with them. Negative 1/3 cubed is negative 1 over 27. 5 times that is negative 5 over 27. Negative 1/3 squared is 1/9. Negative 3 times 1/9 is negative 3/9. Negative 3/9 is negative 1/3. Remember, you have to square it first before you do anything there. 2 times negative 1/3 is negative 2/3. See, that part cleans up. So plus 4. Negative 1/3 minus 2/3 is negative 3/3. That's negative 1. Okay, so just kind of prepping that. It's negative 5/27 minus 1 plus 4. Now, let me combine this negative 1 and the 4 first. Let's get 3. So negative 5/27 plus 3. Or 3 minus, how about I write it that way? 3 minus 5/27. Now, I'm not done. So we have options here. Actually, really one option. I'm going to just do the improper fraction. The 27th number would have a repeated decimal. And I'm not going to write 2 and 22/27, but I am going to do this one. Now, 3 is 81/3. 81/27, excuse me. 81/27 minus 5/27. And there we're going to get 76 over 27, which should not reduce. We're going to be good on that. Excuse me. Okay, so that is that part where we evaluate some functions. Now let's do 17 to 20 where we describe the end behavior of the graph of the function. Now there's a specific format that we use. The order in which you write the formatting's up to you. I'm not going to do it the exact same way as the book will do it, but the same parts will correspond with each other. That's all that matters. So on number 17, excuse me, we have h of x equals negative 5x to the fourth plus 7x cubed minus 6x squared plus 9x plus 2. Now, the first thing you want to check on is make sure you're in standard form. We're in standard form. Now, I'm going to pull out some clues from this stuff for these ones. As we get deeper into these sections, I probably won't write as much as I'm going to do right now. We have a degree of 4. That means it's a quartic, but what's most important for us is it means it's even. It's an even polynomial. And by the way, this is in standard form. I don't know if I mentioned that. This is in standard form. It's even. That's not the answer. The leading coefficient is negative 5. The thing that matters to us there is that it's negative. We have a negative even degree polynomial. Negative, because it's even, it has one of two things that it can either do. It can either start up, finish up, or it can start down and finish down. Because it's negative, it's going to start down, finish down. This is where we describe the end behavior. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. That's the way that we're doing our writings for these things. So, I don't know. I'll start with positive infinity. I don't know if there's a better version or not. As x approaches positive infinity, h of x approaches negative infinity. As this graph, whatever the graph looks like, as it goes forever right on x, we're going to go forever down on y, on h of x. That's the end behavior. As we go forever left, it also goes forever down. That is the nature of an even degree polynomial that is negative. So like I said, I'm going to go slowly through these ones if it's your first time actually seeing these. That's the goal. I want to make sure that you're seeing them as a for sure. This is our answer right here. When they're saying describe the end behavior, that's our description. That's our notation. If you needed to do some sort of layman's term stuff, you're like, I don't know how to write it, so I'm just going to say it out loud, or I'm going to draw a graph that resembles what it would kind of look like. You could either do that, or go as x goes forever right, y goes forever down. As x goes forever left, y goes forever down. And remember, there is some middle behavior of which I don't know what this graph looks like. I'm just making that part up. But there's some middle behavior. The end behavior is what they're talking about. All right, let's go to number 18. Number 18. G of x equals 7x to the 7th plus 12x to the fifth minus 6x cubed minus 2x minus 18. Once again, confirm you're in standard form, or at least that this is the leading term. Yes, it is. A seventh term polynomial, I don't know if it's called a heptic or something like that. I'm not actually sure. Septic? I don't actually. Anyway, degree is 7. That makes it odd. It's an odd degree polynomial. That means it has one of two things that can happen. It can either start down and finish up, or start up and finish down. Which one? It depends on the sign of it. The leading coefficient is also 7. That means it's positive. I'll just put POS. Positive leading coefficient will start down, finish up, right? It's this one. If you're not, you'll go like, how am I supposed to remember which one's which? Well, I guess you can remember. But the other thing is, think about what happens when you plug in a big number, right? Plug in 100. It becomes a big positive number. Plug in negative 100, it's a big negative number. I mean, that's the thing. You plug in big positive numbers, it's going to be a big positive number. You plug in big negative numbers, it's going to be a big negative number out. That's the idea. Anyway, let's write out let's describe it. As x approaches positive infinity, y approaches positive infinity. This is our g of x. So there's that. And as x approaches negative infinity, y approaches negative infinity. Once again, if this were on graph axes, maybe it looks something like that. Forever right, forever up, forever left, forever down is that kind of look. Okay, on numbers 19 and 20, I'm still going to do all the same things, drawings and stuff like that. I'm going to maybe skip a couple little parts to it from what I say out loud. Number 19 is doing something slightly trickier as well. I did state the first thing you should make sure of, which is what? Make sure this is in standard form. Is this in standard form? No. Is it a polynomial? Yes. Is it in standard form? No. So what you want to first do is get a rewrite of this thing. Always. 12x to the 8th. And it's not even just about like, but Mr. Robinson, I see that the leading term is this one because that's the highest degree. I get it. You should still definitely want standard form. This isn't the only kind of thing you're doing with these polynomials, guys. We're going to do factoring with them. We're going to divide them. All these things matter to be in descending order of degree in standard form. You always want standard form, unequivocally. Unconditionally, whatever it is. You always want standard form. Anyway, the degree, this time I'm not going to say I'm not going to write out the thing. The degree is even. That's what matters to me. That 8 is even. The leading coefficient is positive. That's all that matters to me here. Okay? Positive, even. That means it's going to start up, finish up. That's my thing there. So hopefully you see the steps that I kind of skipped with that in mind. That's all that matters to me, the start up, finish up. So we're going to describe it as x approaches positive infinity, y approaches positive infinity, and as x approaches negative infinity, y approaches positive infinity. Now my guess is we've seen an even positive, even negative, and an odd positive. I'm guessing the next one, without seeing the problem, is an odd negative. And that'd be good. It'd be good to hit all four corners of this thing. Number 20. F of x equals 11 minus 18x squared minus 5, also not in standard form, by the way, minus 12x to the fourth minus 2x. Let's rewrite it in standard form. The highest degree we can see is 5. And yeah, this is going to be what I was speculating. Minus 12x to the fourth minus 18x squared minus 2x plus 11. By the way, rewriting things in standard form shouldn't be new for you if you're in IM3, because you took IM2, and that's where we should have stressed a lot of standard form stuff. So me saying that's not that new. But we haven't done many things beyond quadratics before. So having a bunch of terms is like, oh, that's a lot of writing. Do I need to? Yeah, you do. The degree, this is odd. The leading coefficient is negative. All right? An odd negative. That is a start up, finish down qualifier. And by the way, when I draw that stuff in between, I don't know that the graph's going to actually look like that. I can tell you the end behavior will look like that, though, and that's all that matters. Because it's fifth power, guys, it could have gone as much as even like, that. Okay? Who knows? It could do a lot of stuff in between, all depending on the function. You can use a graphing calculator and figure it out. But it starts up, finishes down. As x goes to positive infinity, we go to negative infinity on y. I do need that word as x approaches positive infinity, f of x approaches negative infinity. And then as x approaches negative infinity, f of x approaches positive infinity. Now, like I said, the book does this kind of opposite. They say f of x approaches. They'll actually probably write exact opposite. They'll probably write f of x approaches positive infinity as x approaches negative infinity. F of x approaches negative infinity as x approaches positive infinity. It's probably exactly backwards of how I write it. As long as the parts correspond, you're good. Directionality is kind of a different story there. All right, numbers 21 and 22, we're going to describe the degree and leading coefficient of the polynomial using the graph. So, hey, on 21 and 22, and I'm not going to copy them down. Well, I can copy paste them. But what we're looking for is end behavior and whether they start and finish in the same direction. So we might not know as a for sure what degree it is by number and what the actual coefficient is by number, but we can know whether it's even or odd and what its sign is. Those are the important parts to us. So this has a start up, finish down quality to it. That means two things to us. Because they're opposite directions, that means it's an odd degree. We can call that out. This is an odd degree. Because it finishes downward as x approaches there, it's also negative. So those two things are the qualifiers for us. That's what we're trying to figure out. So describe, well, actually, that's the answer. Odd degree and negative leading coefficient. That's all that kind of matters to us. Do I know the actual equation? No, I don't know it. But yeah, that's the answer. I thought I was going to write some more stuff with it. What we could do is write the end behavior. We could say, as x approaches negative infinity, y approaches positive. As x approaches positive, y approaches negative. Which one does it match? I think that's a little more than just, probably you should only speak about it. Probably shouldn't necessarily need to write about it. And that's it. Yeah, that's what we're doing there. So it's an odd degree, negative leading coefficient. Number 22. Take a look at this guy. There's some turnarounds and stuff like that. Now, there's a way that, and I don't think it's in these problems. Maybe it'll be in a later section. But based on the number of turns, you can say at least what the degree is. But we just need to state whether it's even or odd right now, I'm sure. It starts and finishes in the same direction. That'll make it an even degree polynomial. And the leading coefficient will be positive. The startup, finish up, it has a positive leading coefficient. So I think that's the extent at which is expected for us to state on 21 and 22. Okay, number 23, using structure. Determine whether the function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. Well, I guess I got to copy down the problem. Give me a second. I already see something I got to do the first term. And, oh, okay. Oh, I thought I was going to be able to fit it all. Not even close. Okay. The first term on this thing has x cubed and x there. They're multiplied together. Remember, that's 5 times x cubed times x, and that's to the first power. So don't forget that aspect of it. Now we can simplify just that one little part of it. X cubed times x to the first means x to the fourth power. So you add those exponents there, 5x to the fourth power. I bring that up because you probably saw this part and said, that's a negative, it doesn't work. You got to be careful. That's within its own term. We're going to get to that part. But let's get everything else rewritten just for a moment's time as we arrive at that next, at that term. I do want to see if I can fit this. Negative x to the fifth times x to the fifth. Here, don't worry about the negative right now. The x to the negative fifth times x to the fifth. That is x to the negative 5 plus 5. That is x to the 0. That's minus x to the 0. That's a 0. And then minus 4. So, is this a polynomial? Yes. Now that we simplified that part, negative 5 plus 5 is 0. 0 is a whole number. So it's 4, 3, 4, 2, 1, 0, 0, 0. Yeah, there's still a lot of cleaning up to do here on this one, but is it a polynomial? Yes, it is. Now, we have to combine like terms. We have to get standard form, a lot of things like that. What I'm going to do is write it in descending order of degree. I'm going to rewrite the terms. Well, let's just combine like terms. I take it back. 5x to the fourth minus 9x to the fourth is negative 4x to the fourth. And the highest degree term, the highest degree is 4. The next is degree 3, and I see nothing that can combine with that, so I'll just put plus 5 halves x cubed. Degree 2 is next, this root 2x squared, and I see no other one. 4x is next, and you might say, oh, what about, do I do it with x to the 0? No, remember, x to the 0 is 1. It's just a constant value, so we'll leave that. This is just plus 4x. Now we have negative 1. This is minus 1 here, not 0. Minus 1 minus 4. Negative 1 minus 1 minus 4 is negative 6. This is a weird looking, albeit, this is the polynomial written in standard form. State its degree, degree 4, type, quartic, leading coefficient, negative 4. There we go. Yeah, guys, standard form isn't just descending order of degree. It's also simplifying things. Combine like terms, you know, all that kind of stuff. Everything's got to be involved on it. Number 24. Let f of x equal 13. State the degree, type, and leading coefficient. Describe the end behavior of the function. Explain your reasoning. Now, f of x equals 13. Remember, that means y equals 13, right? That's a constant polynomial. It's a constant. So that means it's a horizontal line like that, 13, crossing at 13. Now, the degree is 0. You have to keep in mind, 13 is 13x to the 0 power. I don't know if they were stating that out loud at any time before, and this is their way of testing you with it now. I've been stating it over and over. It's degree 0. Oh, they did state that once, right, in the very beginning. Type, it's a constant function. That's what it's known as. Leading coefficient, I don't know if they say whether there is one or not. It's either 13 or it's none. Whenever we talk about, we say, here's the coefficient for here. Coefficient's a number that multiplies in front of your thing, you know, whatever. We normally say a constant's not a coefficient. I guess it is when you multiply by x to the 0. I'll call it 13. Leading coefficient is 13. Now, it matters. It makes it positive versus negative, so I'll call it 13. Describe the end behavior. This one's a little bit different, right? And this is as x approaches positive infinity, there are a couple things you could, or not a couple things you could say, but a couple things I could talk about here. First of all, there's no, the y value stays 13. No matter what, it stays 13, whether at 0, at 2, at positive infinity, negative infinity. So the answer is going to be 13 for y when we talk about the end behavior, but we don't say that y approaches 13. I think here we say equals 13, but normally we would say what it approaches. As x approaches positive infinity, y it could approach something. Here it just equals it. I guess that's how I write it. That's how I'm going to go about it. Some people might even say no end behavior. I don't know. It behaves in the end that way. That's what I'm saying. It's always 13. It's always 13. I don't know. They might say approaches 13, but it's not approaching it. It is 13 in that scenario. All right, and exercise is 25 to 32. Graph the polynomial function. So this is where we're going to get into a bit of a table talk, if you will. P of x equals 3 minus x to the 4th. Very first thing I'm going to do in this problem, guys, is rewrite this in standard form. Don't go without doing that, please. Just get to that idea. Because here's the thing. I still want to know the end behavior. I still want to know the degree of the polynomial. I want to know its nature. My expectation, guys, is this polynomial is going to have this kind of look to it. Now, how much does it curve? Does it curve at all in between? I don't know. My concern is the start up, finish down kind of stuff. In fact, it's not going to have, start down, finish down. It's actually not going to have this bump in between because of not having some of those other terms in between. I can actually tell you exactly what this thing's going to look like. It's actually going to look like this. I'm not going to give you the exact points. It's just the general thing. It's actually just going to look like this, and it's going to cross at 3 just because y-intercept, that kind of stuff. So a little different, but what I cared about here was end behavior. End behavior is going to be this. Now, what I'm going to do is build a table of x's and y's. We're going to plug in -2 to 2, and then we're going to plot these points on a graph. I'm going to get this table pre-built for the future problems that we have, because we have 8 of them to do. So I'm going to have that copied and ready to go. Okay. All right. This is where I'm going to do less work overall. Negative 2 to the fourth is 16. Opposite of 16 is negative 16. Plus 3 is negative 13. Negative 1 to the fourth is 1. Opposite of 1 is negative 1. Plus 3 is 2. 0 to the fourth is 0. Opposite of 0 is 0. Plus 3 is 3. 1 to the fourth is 1. Opposite of that is negative 1. Plus 3 is 2. 2 to the fourth is 16. Opposite of negative 16 plus 3 is negative 13. So we have symmetry on this one as well. Let's go ahead and draw this graph by plotting these points. It looks like the tall graph is going to be of more benefit to us for this problem, maybe for some of the other problems. So I'm going to go ahead and use it. I don't know how to best fit this. Give me a second. Let me move the table down here, even if you can't see it in full. I'll get it set in a different way. Actually, let me move it right here. There we go. There we go. You got it all? I got it all. Okay. So yeah, this graph's going to look like this. 0, 3, negative 1, 2, and 1, 2. They won't have this kind of symmetry often. Negative 13 is down here. Like that. So you might say parabola, I guess. A quartic function will not always have the U-shaped thing, though. It will have some bounce back features to it quite often. We could have played with parent function stuff, 1, 1, 2, 16, stuff like that. But no, we're going to have a lot of different kinds of graphs in this. So yeah, that's going to be the graph. They just said graph it. Everything I did leading up to it, okay. But they just did say graph it. Okay, I got to copy that again because I copied the graph last time. Number 26. F of x equals, sorry, that's 27. Number 26. G of x equals x cubed plus x plus 3. By the way, I might have jumped the gun in speaking about I don't ever use a table. Depends on what kind of problems they give you. It depends on if this is factorable and if this has real rational solutions. You'll see what I mean. Otherwise, sometimes you kind of got to force yourself to use a table, I guess. But if I can go without it, you're going to see what we do without a table in a future section. Anyway, this one I expect a positive cubic function to have a nature like this to it on the graph, right? Some sort of whatever like that. Just keep in mind that expectation. Let me do that again. Copy, paste, and drag her down. Let's plug in some numbers. By the way, this is also in standard form already. So let's plug in some numbers. Let me actually start from 0 and move upward to positive. Then I'll go back down to negative in case it's weirder. We got 0 plus 0 plus 3. 1 plus 1 plus 3. 8 plus 2 plus 3. Negative 1 minus 1 plus 3. Negative 8 minus 2 plus 3. So that's my, substitution into those ones. And again, I'm not going to spend longer on that like I did previously if I can get those numbers out well. And if you understand what I'm doing, order of operations and all. So let's see if this satisfies everything we need from that. Negative 2, negative 7 is here. Negative 1, 1, 0, 3 again. We got 1, 5. And 2, 13. Now, the things that I won't know are, does this graph actually have some kind of turn to it? There's a reason that personally I should know whether it does or not. It doesn't look like it does, actually. So I'm just going to leave it like that. But it does have this end behavior. That's all that matters. There is a way to recognize those turns. I was taught it in the past. I should be able to teach it to you guys in the future, I'm sure. I'm just not quite recalling it. I think signs need to change. We might need the x squared with it as well. So this whole, did it turn? No. Does that matter? No. What I was qualifying was end behavior. End behavior. That's all that mattered. So there's the graph. Okay. Before I do number 27, I got to copy the table again. All right, number 27. F of x equals 4x minus 9 minus x cubed. Better rewritten as negative x cubed plus 4x minus 9. It is a negative cubic. That means we're looking more like this right here. Again, does it curve? I don't know. I don't care. I'm looking for the start, up, finish, down stuff. One of the reasons we really need to do this is not just have our table values confirm it, because our table values might not confirm it. I don't know. Oh, I thought I copied the table. Our table, for all we know, going from negative 2 to 2, might be short-sighted. when it comes to long-term behavior. I might only get a certain part of it that, and I have no idea, but I might only get a certain part of it that like it turns down as it goes to the left, and I don't actually ever see it turn back up, right? I might not actually catch that part of it. So keep in mind, having that end behavior is kind of important there. All right, 0. 0 plus 0 minus 9. You might notice that these constants, as long as this is a standard form thing, this is going to be the y-intercept of it, right? That negative 9. Plug in 1. I got negative 1 plus 4. That's 3. 3 minus 9 is negative 6. And then negative 8, 2 cubed and opposite. Negative 8 plus 16. No, negative 8 plus 8. Why did I say plus 16? Negative 8 plus 8 is 0. Minus 9 is negative 9. So you can see there's a little bit of a turn. We'll see if turn down for what. We'll see if it ends up doing what the end behavior speaks on. Negative 1 cubed, opposite of that is 1. 1 minus 4 is negative 3. Negative 3 minus 9 is negative 12. Negative 8, opposite of that is 8. Minus 8 is 0. Minus 9 is negative 9. Okay, I think it will have a little bit of the upturn at the end. I wasn't sure, and it looks like we're going to have it. So 0, negative 9 is here, and then going to the right, we'll hit negative 6, and then back to negative 9. You can see the up and down turn with that. This one actually hits negative 12 here. Whoops, at negative 1, I should say. Boom. And then it goes back up to negative 9 here. There's a little bit of symmetry on this graph, as you can see, but this isn't the entirety of the graph, right? Somewhere it goes back up here. I don't know where. This is all I plugged in, so I can't presume to know. But it does seem to match the end behavior here. Now, the next portion of this I want to talk about is, do we know for sure that this is the relative minimum and this is the relative, not phrases you actually know, but do we know that this is where it actually tops out and bottoms out on this graph? No. You don't know. I don't actually know either. Either a graphing calculator will help me with that, calculus will help me with that, or plugging in more points in between 0 and 1 and 1 and 2 and stuff would help me out with that. So I don't know for sure that it's just hitting those points and that's where it's turning. For all we know, it could actually go up more before it takes its downturn and things like that. It has to make the downturn, but I don't know those are the tops and bottoms. That's the extent to the graph which I'm going to go, and that's partly why we sometimes don't graph using a table, because otherwise we'd have to seek those tops and bottoms, and we just don't have the luxury of seeing those numbers for what they are, if that makes sense. We want to get the general gist of it, and I think that's part of why they're talking about the end behavior. We want the general gist. So this table stuff, like I said, probably not going to be used in future things when we hit graph them. All right, x to the fifth minus 3x cubed plus 2 for this p of x function. It's in standard form. We have a positive odd degree polynomial. We might see something along the lines here. There might be more terms than that. I'm not sure. It's possible. But let's go ahead and go for the table. Go for the table. Close catapult. So we got this guy here, and let's get the graph alongside it. Copy, paste. This program stuff doesn't respond to me all the time. You hear me hit the button, so I'm like, paste, paste, paste. It says no, no, no. All right, 0, you get 2, right? 1 is 1 minus 3. Hopefully you understand that, right? 1 cubed is negative 3. 1, you just look at the coefficients for 1. 1 minus 3 is negative 2 plus 2 is 0. Hey, there's an x-intercept. 2 to the fifth is 32. 2 cubed is 8 times negative 3 is negative 24. So 32 minus 24 is 8 plus 2 is 10. All right, negative 1. We get negative 1 minus 1 plus 3 is 2 plus 2 is 4. Negative 32 plus 24 is negative 8 plus 2 is negative 6. Okay. So negative 2, negative 6. Negative 1, 4. That shoots up really fast, huh? 0, 2. 1, 0. 2, 10. There's definitely an idea of symmetry on these graphs that you can note, but once again, do we know that it actually peaks at that point? No. It has to turn, though. It has to turn there. It somewhere needs to turn here. Does it actually just hit that at the bottom? I don't know. It might have other x-intercepts, right? I don't know. We didn't do enough information, or we didn't gather enough to figure that out. All right, halfway through these. Let's keep moving forward. I don't really know how to go faster on these, considering we have to use the table. Considering we are using the table, I should say. I'm not upset at that. These problems should probably dictate it anyway. It would take quite a bit to do this stuff without the table as well, just so you know. H of x equals x to the fourth minus 2x cubed plus 3x. Already in standard form. It is a positive, even degree polynomial. Looking for something along those lines there. Sure, maybe. There's one thing I'll know for sure about this. Notice it doesn't have a constant, so actually its y-intercept's going to be 0. So that's something I want to fix. Will it turn like that? I don't know. Only one way to find out, right? But that's the end behavior. Important things, end behavior. 0, you plug in 0, you get 0 out. That's the point I was making there. 1, we get 1 minus 2 plus 3. 2. Just plug in 2, you get 16 minus 16, because 2 cubed is 8, times negative 2 is negative 16. 16 minus 16 is 0, plus 6. Negative 1 to the fourth is 1. Then minus 2 times negative 1 is plus 2, so 1 plus 2 is 3. Minus 3 is 0. That becomes 0. Interesting. And then negative 2 to the fourth is 16. Plus 16 is 32. So we won't really be able to fit this one. Minus 6 is 26. Did I say that right? 16 plus 16. Yeah, minus 6, 26. Okay. So this one is interesting, right? Let's see it. Oh, that didn't work. Copy. Paste. Okay, here we go. I won't really be able to fit the 26, but imagine how that's going to shoot up. I want to make sure I did that right as well. Negative 2 to the fourth is 16. I guess so. I guess so. Okay. All right. Negative 1 is 0, and 0 is 0. Now we'll talk about that in just a moment. At 1 we have 2, and at 2 we have 6. Now, being a quartic, again, I don't know where the turnarounds are, but given what we're going to see on this side, remember negative 2 is 26. It's way up there. Given what we see there, keep in mind how sharp this thing's going to go. It is very possible that the graph does this, and I have no idea. I almost want to look at a graphing calculator. The graph doesn't just go here, flatten out, and hit the other. It's going down somewhere before it comes back up, guys. It's going to be sharp, which also means it's entirely possible that this graph now either comes back up right here before taking another downturn and back up like that. It's possible. I think I am going to use a graphing calculator. It's possible that it hits at this peak, probably not, and then goes down before coming back up like that. I'm expecting some other downturn thing. Now, how low does this go? Probably lower than that. I am actually not concerned about that. But I'm guessing it comes back up here, comes back down here, and comes back up at some point. I don't know if it hits the x-axis again. We don't have that information. So again, our graph is still short-sighted information-wise. It's not everything. Doesn't have everything on it. I want to plot this one in the graph thing and just show you the characteristics of what these things can do, and also talk about window range things, right? We got to change some windows here and there. So let's pop this up. Let's do x to the fourth, and I want to make sure I did it right, because I kind of felt like maybe something went wrong. Minus 2x cubed plus 3x. Plus 3x. Okay, if I just hit graph right now, it's possible that we miss some parts about it. Oh. I guess it didn't go sharp down and it didn't curve. Okay, I take it back. It didn't do those things. So that's why I was curious. I didn't know, but I drew what I drew, and that's all that I drew. Anyway. Wah, wah. That was a little bit, oops. Anyway. Yeah, I didn't know what the graph was going to look like. That's the point. But what I drew could work. That could be the quartic. The important part was end behavior. Getting those through the end behavior points, right? And recognizing that that's how it would go. All right, number 30. Number 30. We have 5 plus 3x squared minus x to the fourth. You can already tell I'm going to get into standard form in a bit. But always copy down the original problem. Okay. Negative x to the fourth plus 3x squared plus 5. And what do I do for... Oh, let me copy the table. Actually, I can make another new table. That's lazy on me. Negative, even. Okay, maybe something along those lines. Again, start down, finish down is what I care about there. Let's do a table. X, Y. -2, -1, 0, 1, and 2. Yeah, I don't know why I have to copy and paste a table so badly. That was harmless for me to write. Okay. Plug in 0, you get 5. Plug in 1, you get -1 plus 3 is 2, plus 5 is 7. Plug in 2, we get -16 plus 12, that's -4, plus 5 is 1. Plug in -1, excuse me, -1. And by the way, me skipping, I'm doing this in my head. You don't have to do it in your head. You can write out all the other stuff. Sometimes I'm missing my numbers. When I was doing the whole, this, I know how to calculate that. I was trying to remember what this number was when I did it. That was my problem. So this will be my problem here as well. -1⁴ is 1. Opposite of that is -1. Remember the -1. -1 squared is 1 times 3 is 3. What was this number? -1. -1 plus 3 is 2, plus 5 is 7. So we get 7 there again. And here, we're going to actually get the same thing. -2⁴ is 16. Opposite that's -16. Plus -2 squared. This is also what's just called, this isn't just an even degree function. This is also an even function. -16 plus 12. 12 is -4 plus 5 is 1. So you have exact symmetry on this one because the even function thing. Symmetry across the y-axis. -2, 1, -1, 7, 0, 5, 1, 7, and 2, 1. Based on the end behavior that we see, we expect this to finish downward that way. So this turnaround, and by the way, we don't know where it turns around, right? I don't know that it turns around at that point. I just know that it turns around at some point and goes there. And it's got to bounce back up. It has to bounce back up at that guy, and this has to have symmetry like this. So that's the version of the graph I'm going to draw. I'm sure it goes higher than that and then comes down through there. I'm not positive. I'm just guessing. But there we go. There's number 30. 2 more on this set. Number 31. G of x equals x to the 5th minus 3x to the 4th plus 2x minus 4. It's already in standard form. Yay. Positive quintic, positive odd degree. Finding something like that. Let's see if it actually has some terms. Let's do our xy table. Plug in 0, we're going to get -4. Plug in 1, 1 minus 3 plus 2 minus 4 is -4 as well. Plug in 2, I'm going to write these down. 32 minus 16 times 48 plus 4 minus 4. So 4 minus 4 is 0. This gets us -16. Okay? Let's get rid of that. -1. We'll get -1 minus 3 is -4, minus 2 is -6, minus 4 is -10. Plug in -2. Let's write that down again. We get -32 minus, what was that number? 48 minus 4 minus 4. This isn't a number I'm going to be able to fit on here, but we'll understand that it goes that way. End behavior, right? -80 minus, so -88. I ain't fitting that one. The other ones I barely fit, but thankfully I have the tall graph. So it looks like I'm definitely attaching this tall graph for you guys. It had its meaning, its merit. Okay. 0, -4. 1, -4. Keep in mind the graph's never flat. It's not like we're going to connect this way. We might connect downward like that, or we might connect upward like that. But anyway. 2, -16. It's actually down here. -1, -10. And -2, -88 is way down there, right? But keep in mind the end behavior of this. The fact that these are the only 5 points that we plot. See, I didn't plug in 3. I'm going to plug in 3 for you guys in a second and show you what it is. But let's get the graph beforehand. Keep in mind what the end behavior is supposed to be. It is going to finish down. That's why we go down to -88. And it's got to bounce off this somehow. But at some point, it's got to come back up. It's got to come back up at some point. Now, I don't know if it's by the time that x equals 3. I'll give it a shot. But this is what I'm going to give you for the graph so far. I'll just have it curve off this kind of fast like that. And then it's got to get down here. Maybe it hits us at the bottom. I don't know. But it's got to come back up at some point. It's got to come back up and go that way. This has got to be the nature of our graph. Ooh, I let it go too far over there. but that's got to be the nature of our graph, right? It's got to finish up. So don't lose sight of that. Now, let's plug in 3 and see what happens. Confirm the end behavior. It's got to at some point come back up. If it doesn't, then I'll plug in 4. Plug in 3. 3 to the 5th, this is where it starts to dominate. This is where the odd degree really takes care of it. Guys, 2 to the 5th was 32. You know what 3 to the 5th is? 243. That got bigger. Now, 3 to the 4th, oh, this actually is minus 243. That's kind of weird. And then plus 6 minus 4. Well, guess what that is? That's 2. So, plug in 3, you get 2. So it should be hitting right there. So let me get that part of the graph. But you can see it made its way back up. Those 5 points that we had weren't necessarily enough. Knowing the end behavior was a really great deal for us in understanding, yeah, it's got to finish up. That's why you can't plug in enough table values for it to work. That's why the table for me is not always best to do. And I don't know where it turns, right? I don't know that that's where it turned. Again, I could use a graphing calculator. Let me go to the graphing calculator one more time and vindicate myself a little bit and make this kind of show up in better light for this problem than it did the other problem. Let's do x to the 5th minus 3x to the 4th plus 2x minus 4. Now, when I use the table right now, it's going to kind of shoot up and down. You might not see much of it because you saw what our window did before. There's the crossing stuff. Let me change the x values. I don't care much about what it does to the left and right of -5 and 5, but let's go down for sure to like negative 20. I know it's going to go down beyond that, and up to 10's fine. I want to see these curves. So check this out. It's going to be doing this turnaround stuff, right? So that's, oh, take a look at that. How it even hits 0 and here's 0. Here's 0 and here's 1. This scale's different. It's I compressed y a lot more. X is spread out more. But there's the turnaround of those. And it'll finish down. It's not going to come back up again. It's finishing down after that forevermore. And then this one, it's going up and it's finishing upward. So that's the end behavior of that. It has that kind of turn stuff. Here's our graph in comparison. It looks fine. That's what we got. So hopefully that's kind of making sense as far as how that works. All right, number 32. Last one of the graphs. Number 32, we have p of x equals x to the 6th minus 2x to the 5th minus 2x cubed plus x plus 5. A lot more going on there. The 6 is an even degree. It's positive. It's going to do this and kind of come back around. Now, x to the 6 means it could actually turn more than this many times. Believe it or not, it could actually do a couple more turns. I don't know if it will. I know the plus 5 means it's got a y-intercept there, but let's plug in our esteemed numbers. -2 to 2. See if it's enough for our needs. Plug in 0, you get 5. Plug in 1, we get, literally guys, this is just the coefficients. If you haven't learned yet, it's this. I'm going to put these ones here. It's 1 minus 2 plus 1 plus 5. Okay, because 1 to the 6 is just 1, 1 to the 5th is just 1. So 1 minus 2 is -1, minus 2 is -3, plus 1 is -2, plus 5 is 3. 2 is a little bit trickier. I don't think we can go just based off those coefficients there. So let's, and even negative ones are a little trickier. You have to look at, it's the coefficients. Actually, let me do -1 first. It's the coefficients, these, but the degree matters as far as whether the sign changes or stays the same. -1 to an even power is positive. -1 to an odd power stays negative. So this will be when it's -1. We get 1 plus 2, because the negative times negative. So 1 plus 2 plus 2, that's 5. Minus 1 is 4, plus 5 is 9. It's the 2 and -2 that are trickiest, especially -2. Let's write these out for this, because then I can turn them negative when I need to here. 2 to the 6th is 64. This is minus 64, actually, right there. Minus 16 plus 2 plus 5. So the first one there, 0 minus -14, -9. Now, when I do -2, plug in -2, this will be 64 plus 64 plus 16 minus 2 plus 5. So this will be 128, 144, 142, 147. Once again, out of our window range. And once again, we're a little short-sighted when it comes to seeing end behavior here. I might want to plug in a 3 later and show you where it's going to go, but based on what we understand for end behavior for this problem, we should make an upturn here by the end. So let's plug in the numbers that we can kind of manage. -1, 9, 0, 5, 1, 3, 2, negative 9. And that's all we can fit. Guys, there's a lot more to this graph than we can see. Now, the negative 2, 147 means that I think we were on the right track going here. That we start up do there. Does this do any turnaround in between? Maybe. For the sake of all I can see, I'm going to say I have no idea, so I'm not going to assume that it does. However, this does not finish downward. This needs to finish upward. I don't know if it turns around at this number, but it's got to turn around at some point. It's got to finish upward. Where does it hit when x equals 3? I do not know. Can we try it? Let's figure it out. But that can be the appearance of the graph. Could have it curved in between right here and bounced back down and up? Yes. Did it? I don't know. Probably not. But let's plug in 3. What's 3 to the 6th? 729? I don't know. I'm going to do it on the calculator because I'm going to graph it anyway. So I'm going to type x to the 6. You can watch me on the calculator here. Graphing calculator. I'm going to do x to the 6th minus 2x to the 5th minus 2x cubed plus x plus 5. All right, I'm just going to go to the table and figure it out. X is 3, y is 197. So you can see it shoots up there. But let's go to the graph. Now, I had a graph before that was a different window range. Let's go from, we don't need big numbers on these. Negative 5 to 5 is fine. I don't know how low. Negative 20 is fine, but let's go higher. Let's go to like 40 and see what's going on up there. Or let's go to 20. Let's see what's going on as a whole right now. See, it does a little bit of curve up. Now, obviously, I squished everything on y. It does a little bit of curve up, and I didn't draw that curve up, right? Let's go, actually, let's do my window that I have on my graph. I'll go negative 10 to 10 on x, negative 17 to 17 on y. Keep in mind, this will still be compressed. It'll still be compressed, so actually, that's not going to help much, what I was going to say. But you'll see more of an upward curve on that thing. Just the nature. It actually does an upward curve right there. I didn't have that on mine. Anyway, it does shoot back up. That's the end behavior. We're good to go. I want to make sure that everything I'm doing is also teaching to you guys and making sure it makes sense as a whole. All right. Let's go to numbers 33 to 36. No graphing, it seems. The graph is already there. Next exercise 33 to 36. Describe the x values for which f is increasing or decreasing. F of x is greater than 0 and f of x is less than 0. So it was really good where in the previous chapter, I wasn't describing things in words and I was actually using inequalities. If you saw the lecture portion of this video, you saw that they also used inequalities to do descriptions of these ones. Now, this is just a quadratic. Don't assume it does any turns beyond this. The arrows indicate that exactly. We do see a vertex right here, x equals 4. That means axis of symmetry and all, but what's most important to us is the turnaround of this thing going from decreasing to increasing. We're decreasing in this interval, we're increasing in this interval. So let's first talk about that. We increase when x is greater than 4. We decrease when x is less than 4. Every value of x that's less than 4 to the left of 4, we're decreasing, then we're increasing. The greater than or less than 0 is a different story, right? These are zones for where we're crossing axes. This is where we cross the x-axis at x equals 5 and at x equals 3. When x is, and I want you to see these as zones, if you will. I did this at the time. Not like that. I did this at the time in the lecture portion. I don't know if it made sense to draw them this way, but it's the best way I can point to you. When x is less than 3, we're upward. We're in the upwards region right here. We're positive y values. When x is greater than 5, we're also positive over here. It's when x is between 3 and 5 that we're negative. You can see the negative values right there. So we're positive here, we're positive here, we're negative there. So when is f of x, so this was part A. This was part A. Part B is when is f of x greater than 0? F of x is greater than 0 in the interval when, I don't know if I say when or whatever, or during or something, or on. This is f of x is greater than 0. It's positive when x is less than 3 and when x is greater than 5. I don't know, do I use and? I should probably look this up. Sometimes you got to use like or and things like that. I should probably look that up. But it's on those intervals there. Okay? Now it's negative between 3 and 5. We're going to write that as a compound inequality. X is between 3 and 5. Note that f of x is 0 on x equals 3 and x equals 5. So we don't use the greater than or equal tos and things like that. We just use the less thans because those intercepts are where it matters. So hopefully I can do less weird visual things on that graph to answer the future questions because it might confuse you more than not. Number 34, another quadratic. They start you easy before they hit those little cubic looking ones. But number 34, we got this guy. On number 34, this time for part A, we are now increasing up until x is -4. So from the left of -4, we have the increase. So we increase when x is less than -4. We're decreasing after x equals -4. So decrease when x is greater than -4. That's part A. Let's get rid of those. Let's now talk about part B. When are we positive? We're positive right here. I'm positive that we're positive right there. Now notice these are scaled by 2s. So this is -6 and this is -2. Just keep that in mind. So part B, f of x is greater than 0 or positive when x is between -6 and -2, right? I think that's a better visual for us anyway. Between -6 and -2 on x. And then part C, we're negative on the other parts, right? The y values are negative here and they're negative here. When x is less than -6 and when x is greater than -2. F of x is less than 0. We have negative y values when x is less than -6 and when x is greater than -2. Again, apologies if we're supposed to be doing or something like that. The idea is still in place. I hope the idea still makes sense. Number 35. Yo. All right, now we have a few more intervals of increasing, decreasing, and things like that we have to pay attention to. And yep, this is where polynomials kind of have their messy messes. Yeah, it is good we got this section out of the way before we do the later ones on graphing. I get that. It totally makes sense. I just don't generally use tables. Number 35, we have increases here all the way until x equals 0 and then after x equals 2, right? Those are our increases. So we increase when x is less than 0 and, if we get to use and, when x is greater than 2. We decrease just between 0 and 2. That's a decrease there. Between 0 and 2, the function decreases. Remember, increases and decreases don't have to do with positive and negative. That's why they have those different things that they're asking you. Increases are just when it's going up, not when it's above 0. Now they ask when it's above 0 and below 0, right? That's what they're going to ask on parts B and C. So part B, f of x is greater than 0 where? We're greater than 0 right here and right here. Now, keep in mind, we are not greater than 0 at the x-intercepts. We're at 0 here, we're at 0 here. Got to be very careful with that too. We are not greater than 0 at x equals 2. So f of x is greater than 0 when x is between -1 and 2 and when x is greater than 2, not when x equals 2. That is a 0. That is not a positive part of your interval. F of x is less than 0. We're negative only on this part, right? That end behavior kind of finishes strong there. That's when x is less than -1. There's no other part that we're actually negative. So that would be part C on number 35. Good test of that. Number 36 seems to be the opposite version. In fact, I didn't notice this on, I guess it's not the exact opposite graph on this one, but this almost seems to be the exact opposite graph of the, oh no, it's not. It's slightly different. It's not the exact opposite. What am I saying? It still has the same end behavior. Forget anything that I said. But it has that tangential touching of the x-axis on this side as well. So, spewing nonsense otherwise, I am. All right. Part A. We're increasing. This time I'm not going to draw on it. Let's see. We're increasing here up to -1, and we're increasing after. That's x equals 1. So increasing here and here. So we're increasing when x is less than -1 and when x is greater than +1. We're decreasing between -1 and 1. So -1, x, 1. All right? So just like before, we had two different sets of increases and decreasing was in between. Part B, again, not going to draw anything. When is f of x positive? When are we greater than 0? We aren't here. That's when we are 0. We're 0 here as well. This is the only time we're positive after x equals 2. When x is greater than 2, we have positive f of x values, positive y values. Part C, when are we less than 0? Remember, we're not less than 0 here, but we are less than 0 here, even though we're increasing. We're negative here when x is less than -1, and we're negative here all the way up until x equals 2. So from -1 to 2, we're negative. Less than -1, we're negative. And remember, it sounds weird when I say that, and I say from -1 to 2. That's when x is from -1 to 2. The y values are negative. That's what I mean. Y's are less than 0 when x is less than -1 and when x is between -1 and 2. So yes, my use of inequalities in chapter 2 previously on those descriptions of increasing, decreasing, good times, good times. And there are these things called interval notation. I'm just going to write this right here. You might have no idea what this means at all, but you might write things like this in your classes, all depending. So if you ever see that for like that question, you know, cool. The book's not doing it. So we'll see if you guys do it. All right. Numbers 37 to 40. Actually, here, let me pause for 1 second here. Okay. Sorry about that. All right. In exercises 37 to 40, sketch a graph of the polynomial function f having the given characteristics. Use the graph to describe the degree and leading coefficient of the function f. Yeah, okay, yeah. So we get to be very generic in this sense here. The only thing, I guess I'll use my squared off graphs. You have to keep this in mind, okay? We don't know specifically where the turns are on y. So don't take these things as gospel, right? It's nothing's going to be perfect when it comes to the overall drawing. That's why I'm wondering if I should use these, or, you know, sometimes when I do the graphs, I literally just go like, hey, I got the x and y, you know, and then I just do some things on it. But I like the scaling that we have here. As long as these numbers for x are there, we're good. I don't know if I want to copy these things down. I guess I will, even though they're right there, but let's just get used to the notation. So f is increasing, so we have increasing. Oh, this is how they say it as well. They say when, but increasing when x is greater than 0.5, decreasing when x is less than 0.5. F of x is greater than 0. Okay, so they do use and. Perfect. And they use the words when. So f of x is greater than 0 when x is less than -2 and x is greater than 3. F of x is less than 0 when x is between -2 and 3. Okay. It has an increase and then a decrease. So 0.5 is, for all intents and purposes, our axis of symmetry. Is this really quadratic? I don't know. Maybe. Sure. Whatever. For all intents and purposes, our axis of symmetry. All it means for me right now is it's a line where this thing turns from one to the other. It increases all the way here, and then it decreases afterward, right? It might do some stuff in between and some stuff in between. But it increases forever, decreases forever. Now, this, when x is -2 and 3 are critical points to us. -2 and 3, you want to imagine, are x-intercepts. This is where it changes sign for the graph. So it's increasing all the way here, and it's negative up until, oh, sorry. Oh, I'm sorry, I have this the wrong way. It's increasing when x is greater than 0.5. So I said it the wrong way. It's increasing here, it's decreasing there. Okay, anyway. F of x is positive when x is less than -2, and it's positive when x is greater than -3. So it's starting from the top, starting up, finishing up, right? That's kind of how we say it. And it's negative in between here. Now, it's probably actually a parabola. I'm not going to be cute about it. I'm going to assume it does something there, crosses through there, and it stops its decrease there, and then it comes back up and increases. Now, Where did it decrease? I don't know. They didn't give us that information, right? That's not something we're caring about. What we care about is that it hits the bottom and it hits those parts in between and it goes there. Now, is that a true axis of symmetry? If this is truly a parabola, sure. But all we cared about was this 0.5 being the part where it actually bottoms out. Anyway, there we go. All right, let's go to number 38. And honestly, I don't think copying down the information was very helpful to me. So I hope it's okay that they're just on that side of the problem. We'll just investigate it as we move through the problem itself. So as long as I can fit everything here, I'd rather have a bigger graph than more information typed out. All right, number 38. Now, I might do those dotted lines for turns so we can just get regions of things. So f is increasing between -2 and 3. So again, these aren't axes of symmetry. This is just giving you where our turns are. So it's increasing this entire time here. And I'm going to plot points where I believe x-intercepts are too. It's decreasing outside of those ones. So increasing here, then decreasing here, right? That kind of look. Now, it's greater than 0 when x is, so these are just little clues for now. I'm going to get rid of those in a second. It's decreasing, it's positive when x is less than -4. I'm guessing -4 is an x-intercept. Between 1 and 5. And it's negative and the other part's there. So yeah, it's going to be something more like hitting there and then whatever, hitting these part. I don't know. The graph might kind of look a little bit like that, right? But with curves. So those are the x-intercepts, and those are where it crossed the x-axis, but it decreases. Remember, just because it crosses here doesn't mean it bounces off there. In fact, it doesn't mean that. Remember, it decreases. It goes through there as it decreases, and it bounces off that when I hit this green. Boom, like that. And then at some point it's going to increase. Let's try that again. Boom. And at some point it's going to increase. It's going to go through this point, and it's going to bounce off that one, and then it's got to come back down and hit like that somewhere. Go like that. Now I kind of messed up on this part. It didn't quite bottom out here. Boom. Got to do it more like that. So hopefully you're investigating this with me the right way, and it's starting to make sense as far as what we're doing. What's the actual bottom and top? I don't know. They didn't give us the information. That's not the important part. And that's kind of what I want to keep stressing with you. That's not the important part. The only important part is this other thing here. I want to see on the next two if we can do it without any visual cues along the way, that we can just draw it and go. I like the visual cues, don't get me wrong. I want to see how much we can do without it. I might do the intercept still, but I need to turn at those points. Because the thing is, you might not be able to have the luxury of being able to draw these dotted lines and things like that. So I want you to just be as ready and in the know without all the visual cues that I have, right? But you can do x-intercepts, that's for sure. And generally we will. Generally you'd want to plot the x-intercepts first. So number 39, it's increasing between -2 and 0. I might want my visual cues. And when x is greater than 2. It's decreasing when x is less than -2 and between 0 and 2. Okay, that's a lot of things to keep in mind. Okay, I am going to plot the x-intercepts at least. When x is less than -3, so I believe -3 is an x-intercept, between -1 and 1, and when x is greater than 3. So these seem to be x-intercepts, so we're positive on some of those things and then negative on the others. Okay, so I want to look at the end behavior first. It's positive when x is less than -3, and it's decreasing all the way down until -2. So I'm looking at the leftmost decreasing thing. It's coming from the top and going down until -2, then it turns around and it starts to increase. So I have that part. At -2, we start our increase. And it increases all the way until 0. So it's going to go through here. It's going to increase from -2 to 0 is what it states. Now, what's the actual y-intercept? I don't care. From -2 to 0. It decreases again from 0 to 2. So it's probably just going to be like this, like symmetrical. Decreases from 0 to 2, and it increases the rest of the way when x is greater than 2. So I'm just going to give it some symmetry like that, good old W shape. That's probably a good expectation of an example like that. So yeah, working left to right is nice. In saying that, I just said, hey, let's work as far left as possible, figure out when it hits its increases and stuff like that. That actually worked out. Okay. And then number 40, now you know what else you can do is you can draw some of those arrows here and have them in mind before you actually get them drawn. So you can probably do things like that. There are a lot of visual cues you can do, guys. As long as you use some erasing after, I suppose. All right, last one here from these, number 40. I like these problems. They're fun. Number 40, let's figure out what our intercepts are. I won't stop doing the intercepts. I think that makes a lot of sense. F of x is greater than 0 and between negative 1.5 and 0. So here's negative 1.5. Here's 0. And 1.5 is another value. Those are the only ones that seem to be x-intercepts. Those are critical points when they say we go positive, negative, stuff like that. Now let's look at where it has moments of increase and decrease. It says that the leftmost, when x is less than negative 1, it's increasing that entire way. So all the way up until negative 1, it's increasing. That means it's coming from the left side, or from the left side, it's coming from that bottom. Boom, it's coming up through. And at negative 1, it stops its increase right there. It's going to decrease from negative 1 to positive 1. So it's got to hit through that 0. Oh, I didn't check on negative and positive. It's positive between negative 1.5 and 0, so that makes sense. It's just going to boom right there. It's going to continue decreasing from 0 to 1.5. Or it's going to be negative from 0 to 1.5, and it's going to keep decreasing all the way until there. Excuse me, it decreases until 1. It decreases until 1, but it's negative until 0 to 1.5 like that. And then it's increasing the rest of the way when x is greater than 1, and it's positive past x being 1.5. So like that. You know what kind of problem I was expecting to see and we never did? Was one that, I'm just going to make this up, was one where it says it's positive when x is less than 9 and greater than 9, but it decreases when x is less than 9 and it increases when x is greater than 9, that you have to do a kiss off like that and do that kind of stuff. We didn't get one of those here. Maybe there's a trickier problem later that has something like that, but not right here. Okay, they all only asked us to graph on those, right? Because that's all I really did. Sketch a graph, use the graph to describe the degree. Oh, I didn't do those. I guess I got to go back on the problems. Guys, I am so sorry. Let's go back to these ones. So number 37, I have an even degree and a positive leading coefficient. Sorry about that. Here I have an odd degree, an odd degree, and a negative leading coefficient. I guess I should have looked up the things here. Here I have an even degree, starts up, finishes up, and a positive leading coefficient. And here I have an odd degree and a positive leading coefficient. Sorry about those. Okay. Number 41, modeling with mathematics. From 1980 to 2007, the number of drive-in theaters, oh, I miss drive-in. Actually, I have a drive-in theater kind of nearby me, but I missed just the events. The number of drive-in theaters in the United States can be modeled by the function d of t, oh, we're going to use a calculator, equals negative 0.141 t cubed plus 9.64 t squared minus 232.5 t plus 2,421. Where d of t is the number of open theaters and t is the number of years after 1980. Normally they say since 1980. Does that mean, okay, I guess when t is 0, that means 1980. That means to interpret something for you, I don't know if we have to interpret it here, it doesn't look like it. To interpret it, in the year 1980, there were this many drive-in theaters, according to the model. Because that would be when t is 0. Okay. Use a graphing calculator to graph the function for the interval 0 to 27. Describe the behavior of the graph of this interval. All right, so I'm going to go to my graphing calculator. We are going to type in that stuff. Now, t is going to have to be an x on here, but negative 0.141 x squared. I'm just overwriting, or cubed. I'm overwriting my other one. Plus 9.64 t squared minus 232.5 t plus 2421. All right, I'm going to do a window range from 0 on x to 27. I don't know what y ranges it'll hit. Clearly, it'll hit somewhere in the 2400s or 2400s. I don't care about negative y values here, so I'm going to go at least 0 to, let's see, 3000, because it might go up after that. We might hit the bottom end of the curve where it goes down. Maybe it shoots back up. I don't know. Let's see. So let's graph it. It's just bottoming out. We don't get, yeah, we're losing drive-in theaters. Remember, this is a cubic function where end behavior-wise, listen, this graph, guys, as a whole is probably doing something like this, right? We're probably looking at the snapshot right there on it, as far as I can tell, right? We're probably looking at this on our graph, and that's all that we can see. Just keep that in mind when it comes to this cubic. Anyway, remember, the model only applies to just specific parts. So there's the graph. Describe the behavior of the graph on this interval is the question. Okay, so here we go. This is part A. What do we see? A decrease in drive-in theaters over this time. Over the course of these 27 years, we are seeing a decrease in drive-in theaters. However, what do you see? There's a slowing up of the decrease. So when we go back here, it's sharper. I don't know if I'm going to investigate all the numbers here, but it's a sharper decline, you know, for the first, I don't know, these years, 7, 8 years or so. And then you see it slow up a little bit more, right? It's kind of sharp there and kind of eases itself up. It's doing it more over time anyway. I'll just say that it eases up over time. So for the first whatever years, it's doing a little more so and then a little less so. It's kind of up to how you want to say that. So, however, can't see this. However, the rate of decrease is slowing up over time. Now, there are a couple reasons for that. There are some drive-in theaters that will just remain open, period. There are only so many drive-in theaters you can close in general, right? Some people flock to others and it gets bigger business. We're not really stating why that's happening unless they ask us, but those could be reasons. It's not always constant. Part B. What is the average rate of change in the number of drive-in movie theaters from 1980 to 1995 and 1995 to 2007? Interpret the average rates of change. Well, that's where what I was saying is going to kind of come into play here. Whoops. Ignore that completely, guys. I clicked on the wrong thing. That was a Zoom thing. Anyway, let me get a snapshot of just the graphing calculator just for a moment. So I just got a snapshot of it. It's kind of random. But we're going from, you know, we're looking at the slope from 1980 to 1995, wherever that is, and then 1995 to 2007. What you're going to see is a larger average rate of change at one part and a lesser average rate of change at the other part, right? So that's just the idea of it. That's not obviously me doing the calculations. I'm going to do the calculations, and I'm going to use the calculator, but we're going to plug those numbers in. So for part B, we got to find the slope. This is for 1980 to 1995. Whoops. From 1980 to 1995. And then we'll do 1995 to 2007. This is average rate of change. So we got to do D of, now remember, 1995 is 15 years after 1980. So D of 5 minus D of 0 divided by 15 minus 0 is what's going to happen there. We're going to take our rise over our run, or fall over run in this case. From 1995 to 2007, we're going to be doing D of 27 minus D of 15 over 27 minus 15. Now, the very first things I can already do for you is 15 minus 0 is 15. 27 minus 15 is 12. D of 0, we should know, is 2421 right here. Everything else I have to kind of get computed. So this is where I can use the calculator. I'm going to write it down. I need to figure out two things, D of 15 and D of 27. And obviously, we'll divide it as well. So I go back to here, and we're going to have, I'm going to go to the table, and I'm going to ask for values. I'm going to ask for 15 and 27. And I'm going to write these numbers down. Oh, and they're strange decimals, but of course, we're going to get some things in. Actually, they look exact, though. So 27 is 3 95.757. 15 is 626 point, what was it? 625. Okay, so I didn't expect the numbers to be so sorry, I'm writing them right now, but I didn't expect the numbers to be so large with decimals, so I have to kind of refit everything. All right, so I'm trying to fit it a little bit. Here's what I have so far. Trying to fit this one. I try to extend this one a little bit. All right, so this is what I'm going to compute. So I'm just going to do that in the calculator. Just give me a second. So 626.625 minus 2421, and then divide that by 15. So over the course of those 15 years, we're averaging, I'm going to write the exact number to start, negative 119.625. And then this one, we're going to get 395.757 minus, I won't round anything until the very end, and even then I want to see what I'm supposed to interpret. And then this divided by 12. So this should be a smaller number, a lesser. Negative 19, whoa, significantly less. Oh my goodness. Did I type something wrong on the other one? Maybe not. Negative 19.239. Wow, significant difference here. So it says, what's the average rate of change there? Interpret the average rates of change. Okay, so to interpret these, so negative 119.625, I'm going to round that to negative 120, right? From 1980 to 1995, there was an average, let's see how they said it, drive-in theaters. The number of drive-in theaters on average decreased by 120 theaters, or by 120 every year, yearly. So I'll say the same thing for the next set, just kind of change the numbers. From 1995 to 2007, it decreased significantly less, by about 19 yearly. That's the interpretation. Significant change there, right? That's where interpreting the graph showed the slow up in that nature. So that's part B. Part C. Do you think this model can be used for years before 1980 or after 2007? Explain. This is one of those things where we might want to zoom out more. We have the graphing calculator. Let's do more of a zoom out. Let's give us a little more X's. Let's give 5 years before. Let's give 5 years after. Let's give 10 years after. Let's see what's going on there. We probably need some more Y values as well. I don't care about the negatives so much, but I want you to see what's going to kind of occur. I definitely need them to be positive. Let's get like negative 1,000. And let's get like 6,000. I think we're going to need some of this. We probably won't even hit what it's hitting there because it's going to curve up so much. Look at this snapshot. Oh, maybe we will. Is it going to curve back up? Oh, it's still, okay. You know what? This doesn't actually have the curve up of the cubic, but that is the part of the cubic that we had there. But eventually it's lessening itself to the point by year 35 or whatever, it's done. It's cooked. So can this work? I mean, what we need to understand is they created the domain for a specific reason. That's probably the best shot of the model that would work out. But you can see by year 35 or so, we lose all drive-in theaters, which is maybe reasonable. So we'll kind of say the same thing. You know, the lecture had something like this as well, and I can kind of say the same stuff here, which is what? It's outside a few years before and after this model takes place can be considered reasonable for the overall number of drive-in theaters. However, at some point earlier on, you have more drive-in theaters than the world knows, right? Than the world could contain. Because remember, it literally goes to infinity. And after 35 or so years, you lose all drive-in theaters and go negative. Meaning around 2015. So around 2015, maybe 2016, I think. Around 2016, you lose all drive-in theaters and go negative, which isn't possible. Now, it's possible to lose all drive-in theaters, and by and large, we kind of nearly had. I thought they just got rid of them as a whole. Maybe there are only 4 in the world that no, there are probably still like 400. But, you know, that idea is just that it doesn't work in full. So, as a snapshot, I could zoom out a little bit and be okay. I think I can. At some point, as a far zoom out, no. If I zoomed out a little bit, like by a little bit more, I mean a lot more. If I zoomed out more as far as like, let's just go like -30 and really hit high up and really down low. And let's go down to, say, 50 at least. Now you get more of the cubic look of this thing. Now, it doesn't have much of a curve that way before it goes down, but the end behavior, oh, I need more. The end behavior here is a downward turn on your cubic, right? It's going to go up to positive infinity right here, and it's going to go down to negative infinity right there. So, right, cubic function does cubic function things. Okay, that's number 41. Number 42, problem solving. The weight of an ideal round cut diamond can be modeled by this. Let's do graphing calculator stuff. Where are the, oh, I thought there were multiple parts. I'm like, where are parts A, B, and C? Are they on the other page? All right, number 42. W equals I got to make sure to fit all this. Oh, got it. That's a decimal, 0.01. Okay. Bad handwriting. W is the weight of the diamond in carats, and D is the diameter in millimeters. I'm interested to figure out how that works. According to the model, what is the weight of the diamond with a diameter of 12 millimeters? Well, this is just a substitution, guys. Not really a word problem as much as, you know, whatever else. Unless there are more questions on the other side, which is doubtful in this situation. So I'm going to go to the graphing calculator again. And especially if they ask more questions, I would plug it into here. But this is probably even faster to still type it this way than just typing 12 itself. X cubed, that's all good. Minus, I can't see the equation. Minus 0.0125 x squared plus 0.022x minus 0.01, delete that guy right there. Okay, so I'm just going to go to the table set thing. I'm going to ask it 12, delete these ones, 12 millimeters. I think all the units are in place still when it comes to weight. The weight is in carats, and this will be an 8.5 carat diamond. So W of 12 is about 8.5 carats. And I think that's all you have to do. Just a substitution. Spelled carats kind of strangely. That is an A. I just didn't write it well. All right. That's number 42. Let's keep going. Number 43, abstract reasoning. Suppose f of x approaches infinity as, oh, hold on. I want to write this the way that I write it so I can kind of see it. As x approaches, let's actually start with positive infinity. As x approaches positive infinity, f of x approaches negative infinity. And as, you can read it, you can see it however you like. As x approaches negative infinity, f of x approaches positive infinity. All right, so we go right and down, and we go left and up. Describe the end behavior of g of x equals negative f of x. So for g of x equals negative f of x, you have to keep in mind that, and this is where we're going to get in some of the transformation things later, this is a reflection over the x-axis. That means a graph, because this graph here would take on what appearance? It would start left and up and finish right and down. It would look something like this. Well, you know what g of x equals negative f of x would look like? Do you know? Because I'll tell you, I'll show you. You flip it over. You flip it over like that. So that's what's going to happen in a situation like this. So I'm going to copy and paste this and get this ready. So with the 43 and all, or make it look like 13. So here, as x approaches positive infinity, now f of x approaches positive infinity. So this will now be positive, and this will now be negative. It says justify your answer. This is a reflection. I'll just state it in that way. This is a reflection over the x-axis. So your y values change. This is, or G, the graph of G is a reflection in the x-axis from f. Therefore, the y values will change sign. If they change sign, then f of x changes end behavior. And that's it. Okay, number 44, thought-provoking. Write an even degree polynomial function such that the end behavior of f is given by f of x. Oh, I want to write this kind of in the way that I do it. So I'm going to copy and paste this again, get it ready. I don't know if this is the exact way that it's written, but I'll get the template set. So 44, such that as x approaches negative, y approaches negative, and as x approaches positive, y approaches negative. So negative here and here. Justify your answer by drawing the graph of your function. Well, I'm not going to use tables. Well, I think I have to use tables. So, all right. Even degree function such end behavior. So what we need is even degree. We can, well, you know what? I can do a quadratic. I don't have to do a quartic. So even degree. And what do I need here? I need a negative leading coefficient. Negative LC. I'm going to do just a quadratic. That way I don't have to use a table. So I can say, and I can even use, heck, I can even use vertex form or something like that, right? Now, you know what? I think they want us to get a little more robust. All right, I'm going to do something like this. I just don't know how big it'll get. Negative x to the fourth plus 3x squared minus 2x plus 5. I don't know if these numbers will look good, bad, I'm not sure what. But this one should have that end behavior like this, and we'll sketch the graph. So yes, I torture myself in this way, and that, I don't know if it makes it better or worse. I would cheat if I just used a negative vertex form quadratic, basically. I think that's cheating too much. And this enforces some more table usage as we saw before. Let's confirm that this works as it would. We plug in 0, we get 5. You plug in 1, you get negative 1 plus 3 is 2. You get 5 as well. Okay. You plug in 2, you get negative 16 plus 12 is negative 4. Minus 4 is negative 8 plus 5 is negative 3. You plug in negative 1, you get negative 1 plus 3 plus 2 is 5 plus 5 is 8. Well, hold on a second. Negative 1 plus 3 is 2 plus 2 is 4 plus 5 is 9, I think. And then I think it's just, oh, it might go down again. Hopefully it does. So this will be, let me write this one out. Negative 16 plus 12 plus 4 plus 5. Oh, it didn't go down yet. Might have to plug in negative 3 because it says justify by drawing the graph. So that one didn't go down yet. That's at 5. Why did... Hold on. Let's plug in negative 3. I'm going to go until it goes down. All right, plug in negative 3. We're going to get, now it should go down, negative 81 plus 27 plus 6 plus 5. All right, 27 plus 6 is 33 plus 5 is 38. Negative 81 plus 38 is negative 43. So negative 43. There's the downturn. So, yeah, man, these functions, when they want to change direction, whoo, they fly in the other direction, I tell you. This didn't copy and paste. Hold on. Copy. You got me? Paste. You got me. Okay. So let's confirm the end behavior here, I guess. I mean, I'm not doing more than that. I could have used the graphing calculator. Yeah. 1, 5, 0, 5, negative 1, 9, negative 2, 5. I kind of like this one. 2, negative 3, and then negative 3, negative 43 I can't fit. But you can tell it's going to go down forever after that. So yeah, this graph kind of has that nice shape thing that I like to kind of show and demonstrate, and does this up and downness. This is going to do some form of this right here. It's got to take these and hit them at some point, right? It hits two things of the same height. Ooh, I do not want to go vertical there. But it hits two things of the same height right there. So it's got to, make an upturn to go get it. Or, it might flatten out a little bit, but it's not a true flattening out. So probably something like that. So there's the end behavior of that one, number 44. It was an open-ended question. Number 45, using tools. In section 1.2, exercise 12, sure, the function v equals 4/3, oh, I remember that, times quantity pi plus 4 represents the volume v of the tank. I remember that, factoring that out and writing that. Anyway, so let's see, v equals 4r cubed times pi plus 4. Yeah, I remember having the thing. Anyway, you can find my video on it. Use a graphing calculator to graph the function. Estimate the percent change in volume when r increases from 1 foot to 1 foot 1 inch. Is the percent change greater than you expected? Explain. I don't know. Okay. First of all, I don't know. I guess we assume r is in inches, okay? So an r of 12 inches versus an r of 13 inches. Please note that 1 foot is 12 inches, 1 foot 1 inch is that. That way I don't have to say 1.1 or 1 point whatever that is. Anyway, so these are the two different r's we're going to be looking at some point. Now I'm going to use my graphing calculator for that. Those are the numbers we're going to plug in. So let's go to the graphing calculator here. Let's do 4r cubed times pi plus 4. Keep in mind, whether it's distributed or not, it's still a positive cubic function. So we're going to plug in 12 and 13. Now, I expect, now remember, this is going to be, wait, what is percent change? The percent change, you have to, I'll show you what you do on percent change. But I expect it to be a pretty massive change. One of them is going to do 12 cubed. One of them is going to do 13 cubed. Guys, these aren't small numbers. 12 cubed, we just saw it earlier. It was like something 70, it was in the thousands, and 13 cubed as well. I expect, let's see, can I predict this? Not really. I predict like a 60% change. I expect something massive. It's probably going to be even bigger than that, but I predict a 60% change. So I'm on ask mode. I'm going to ask 12 and 13. So these are the different volumes. Let's write those ones down. Okay, maybe it's not that big of a change. It's more like a 30% or something like that. I don't know. Anyway, let's see. Let's write those ones down. V sub 12, and remember, this is in cubic inches, but it doesn't matter. 49363. I'm sure there are decimals. I'm not concerned about them. I'm just writing their rounded numbers. That's going to be enough of what we do here. V sub 13 is 62760. Now, the percent change portion of this is going to be when it increases from one to another. It says, how much was it originally, its total, that was V of 12, and how much is new. So percent change is going to take the difference in these two, V sub 13 minus V sub 12, and divide it by the original V sub 12 to say how much did we change from this to that. Like if you go a percent change from 4 to 6, that's a 50% change because 6 minus 4, all divided by 4 is 2 out of 4, which is 0.5, and that's how that works. So this is going to be 62760, and I know there were some decimals. This time I'm actually not going to care about it. Over 49363. So let me do that in the calculator. Give me a moment. 62760 minus 49363 divided by 49363. Did I type it right? 493. Okay. 0.2713. So around a 27% change. Okay. Most people would probably have expected something smaller because from 12 to 13 is a very small change. I over-exaggerated the whole 60% thing clearly. It was about half of it. So I'm not going to write on here I expected more. We're supposed to expect less. It's the cubic thing really that's taking hold though. That's the dominance of something being cubed. You just saw it on this last problem. You remember when we didn't yet see the change over here on how this was going to look to really go forever down? I guess we saw the downturn, but this is where we saw it. We just went one number different. Boom. It went from a difference of 4 to a difference of 48 in the change of just in the same constant change on x's. So that's where we really can see how cubic functions or higher degree polynomials can really make a drastic turn or increase. Anyway, was it greater than I expected? Sure. I expected, I mean, I can pretend and say that, but I expected less of a percent change because 12 to 13 isn't that much. In cubic sense, though, it will change a lot. All right, number 46. Your friend uses the table to speculate that the function f is an even degree polynomial and the function g is an odd degree polynomial. Is your friend correct? Explain your reasoning. So what I'm seeing is an n behavior thing, and I'm assuming it's taking that n change how it is. It's starting up and finishing up on this one. That's what an even degree polynomial would do. This one starts up and finishes down. An odd degree polynomial would do that. What did they say? F is even, g is odd. I agree with friend. Our friend, I think, was wrong in the entirety of chapter 2, or at least it seemed like it. They were on a streak of like 4 or 5 sections in a row. Now your friend's actually correct in this chapter, in this section. Let's see if they stay correct in this chapter. My friend appears to be correct. The end behavior of f starts, when I say starts and finishes, starts and finishes, I mean from the left side and the right side, in the same direction, positive, much like an even polynomial would, or much like an even degree polynomial would behave. Likewise, the g starts and finishes in opposite directions. Now, it doesn't matter which directions they are as long as they're opposite. It started positive, ended negative. I guess it's a negative odd degree one. Much like an odd degree polynomial would behave. So, yep, your friend seems correct in that way. Looking good, friend. Maybe it's a new friend for this chapter. The other friend flunked out after so many. All right, number 47. 4 more questions. Drawing conclusions. The graph of a function is symmetric with respect to the y-axis if for each point a, b on the graph. Okay. Negative ab is also a point on the graph. If for each, I guess I had to read the whole sentence. The graph of a function is symmetric with respect to the y-axis if for each point AB on the graph, negative AB is also on the graph. Yes, this is how even functions behave. It's a way of saying that there's perfect symmetry. We drew one like this. There's perfect symmetry, boom, like that on both sides of the graph. If there's AB, there's also a negative AB. Same distance from the y-axis and the same height, that kind of thing. Now, I don't know if this has anything to do with the problem. That's what they're saying, though. The graph of a function is symmetric with respect to the origin. So there's the first part. The graph is symmetric with respect to the origin if for, and I know how this works, this is called an odd function, not odd degree. This is called an even function, not even degree, although all even functions are even degrees. This is an odd degree function here. For each AB, there's also a, negative B. This is symmetry across the origin, like this, something like that. If there's an AB, there's a negative B. Now notice that you're like, wait a second, that B is not negative. B can be a negative number. B can be -3, and the opposite of -3 is +3, so it totally can. They're just saying there's symmetry on those parts. Anyway, this isn't answering the question. This is describing to you what they are saying in a visual way. I'm giving a visual sense of what they're talking about. As far as phrasing or as terminology goes, this is known as an even function and an odd function, just so you're aware. Anyway, let's see what they do with this. Use a graphing calculator to graph the function y equals x to the n power when n is 1, 2, 3, 4, 5, and 6. In each case, identify the symmetry of the graph. Look at me. I'm the graphing calculator now. I'm going to go ahead and show you those ones right here. So for y equals x to the n, let's see when n equals n and y. I guess n is what matters here, right? X is the x. Sorry, not y. I don't want to say y. I want to say symmetry. Symmetry. Do they call them odd and even? What do they call them? They say symmetric with y-axis and x-axis. I'll just say symmetry across y-axis or origin. I'm going to draw them for you, though. Sorry about that part. All right. Symmetry. All right. When n is 1, 2, 3, 4, 5, and 6. So here's what it's going to look like on each one, okay? Let's do boom, boom, boom. When x is 1, now remember, this is just x to the n. This is the basic parent function type, right? This is just y equals x. That's going to look like this. It's going to be a straight line. It's going to go through the origin. It's going to go through the origin. That means we get an AB, boom, and a negative A, negative B, boom. That has symmetry across the origin. Whoops. When n equals 2, it's a parabola. We've seen a lot of x squareds, right? 0, 0, 1, 1, 2, 4, 3, 9, both sides like that. This is symmetry across the y-axis. We've seen these axes of symmetry, right? So that's y-axis. When x equals 3, it's a cubic function. When you cube negative numbers, you get negative numbers out. It's got some sort of curve to it. 0 cubed is still 0. Remember, all these, they'll cross through the origin as for sure, but what else does it do? It turns negative on this side where it stays positive on that side. It should be sharper than that, but it's got an origin symmetry as well, because negative's negative, it's positive, positive. To the fourth power, now we raise negative numbers to the fourth power, and they become positive again. So it's another parabola. It's a different kind. It's a little less sharp between negative 1 and 1, and then it's sharper at those parts, but it's going to look like your parabola bits. And then this goes on to be exactly as you see for those. Odd degree ones are symmetric across the origin, and even degree ones are symmetric across the y-axis. Just kind of take my word for it, or understand raising negative numbers to odd powers makes them negative. They ask us to explain? No, just identify the symmetry part A. Part B, oh, here we go. Predict what symmetry the graphs of 10 and 11 have. Explain your reasoning. So I kind of just stated it on that part. That's where I did 5 and 6. I didn't actually put them into play, but when x is 10 versus when x is 11. X is 10, we expect y-axis. It's an even degree. And this one, we expect origin. So let me type it over here. Even degree. When n is even, raising negative numbers to said power turns them positive and creates symmetry on y-axis, across y-axis. Therefore, when n equals 10, we predict, and it's correct, y-axis. Odd degree, I'm going to run out of room. When n is odd, the function stays, oh, I can't drag it anymore. Let's see. There we go. When n is odd, when n is off, when n is odd, negative inputs have negative outputs, which symmetry across the origin has. I'll shrink it. So when, I just want to stay on the lines. Therefore, when n equals 11, we predict symmetry across the origin. All right. Okay. Lots to type out there. I tend to overtype. I hope that you kind of tend to write less, use more paraphrasing, something like that. That's me. Okay, number 48. How do you see it? My question is, how long have we gone? Oh, wow. Oh, jeez. I didn't know that. 2.5 hours. How do you see it? The graph of a polynomial function is shown. A, describe the degree and leading coefficient of f. Okay, I see this as an odd degree and positive leading coefficient. Part B, describe the intervals where the function's increasing and decreasing. I see it increasing all the way up to -3, so when x is less than -3, and when x is greater than -1. I see it decreasing between -3 and -1 on x. -3 and -1 on x. Part C. What is the constant term of the polynomial function. Constant term, if you notice, guys, that's the y-intercept. So in this case, it's going to be 4. So the constant term is 4. That's the value of y when x equals 0. Okay? Number 49, reasoning. A cubic polynomial function... Ugh! Oh, fish. A cubic polynomial function f has a leading coefficient of 2 and a constant term of -5. LC equals 2. Oh, look, constant term. We just talked about that. Constant equals -5. That means we know that in our equation, and they say cubic, so cubic, that means we know it's some f of x equals 2x cubed. That's the leading term. It's cubic. Somewhere it's -5. It's possible we have some sort of, what, ax cubed plus bx squared plus cx plus d, like that. This is our thing. And that's what they show us. When f of 1 is 0 and f of 2 is 3, what is f of -5? Explain your reasoning. Well, that's an x-intercept. Well, here's what, okay, so here's what this means to me. When f of 1 equals 0, that means when x is 1, y is 0. When f of 2 equals 3, that means when x is 2, y is 3. I think given what we have here, I guess there's probably enough information to create a system of equations and solve. Because b and c will be our only variables. We're going to plug in 1 for x, 0 for y, 2 for x, 3 for y, and come up with equations. I think we can do that. They're saying what's f of -5? We need to come up with the equation. We have to figure out what b and c are here. So let's do this. We've done this in section 2.4, systems of linear equations, solving them. And don't treat this as a system of 4. Even though there are 4 parts, we're going to plug 1 into these. So 2 times 1 cubed is 2, plus b times 1 squared is b, plus c times 1 is c, minus 5 equals 0. F of 1 is 0. And then 2 times 2 cubed is 16, plus b times 2 squared is 4b, plus 2 times c minus 5 is 3. So here's our setup for our system. Let's keep moving on. 2 minus 5 is -3. Add that over, you get 3. So b plus c equals 3. 16 minus 5 is 11. Subtract 11 over, you get -8. So 4b plus 2c equals -8. I'm going to divide that bottom equation by -2 to now solve this system. You get -2b minus c equals 4. Ignore that now. And we add down these lists and we get -b equals 7. Therefore, b equals -7. Okay, we'll use that to solve for c. If b is -7, -7 plus c equals 3. Therefore, c equals 10. So my equation for this function is f of x equals, I think leading coefficient was 2, minus 7x squared plus 10x minus 5. Okay, if that's our equation, they said, what is f of -5? So now we substitute that. And we can go back to what we did at the time. 2 times -5 cubed minus 7 times -5 squared plus 10 times -5 minus 5. I'm going to try and do this without a calculator. -5 cubed is -125 times 2 is -250. -5 squared is 25 times -7 is -175. Ooh, it's getting largely negative. Minus 50 minus 5. So that's -425, -470, -480 is my value for f of -5. I don't know if it's right. I mean, I'm not saying I think it's wrong, but Okay, and the last problem, number 50. The weight in pounds of a rainbow trout can be modeled by y equals... that trout. Y equals 0.000304x cubed. Sorry about the spacing. Where x is the length in inches of the trout. Write a function that relates the weight y and length x of a rainbow trout when y is measured in kilograms and x is measured in centimeters. Use the fact that 1 kilogram is 2.20 pounds and 1 centimeter is 0.394 inches. All right, let me write those. So 1 kg is 2.20 lbs and 1 centimeter is 0.394 inches. So yeah, to compensate, you take whatever inches you have, you multiply by 0.394, take however many pounds, multiply by 2.20. So modified equation of this would look like I'll try 2.2. 2.2y is 0.000304 times 0.394x cubed. I guess ideally what you want, they said y in terms of x or whatever, right? So we have to divide by 2.2, but I also want to cube that 0.394. So the way that it's eventually going to look is like, I'm going to calculate it, but 0.000304 times 0.394 cubed times x cubed, right? It's kind of, you have both of them there, and you're going to divide this by 2.2. I'll put the x cubed as like its own thing. X cubed like that. So I need to figure out what this number is, basically. That's going to get me, this is part A. Part A. So this is going to get me that number. Should be small. 0.000304 times 0.394 cubed divided by 2.2. Okay, this, if your calculator does the same thing, we're using scientific notation there. So what we need as an answer there is I think I need 5 zeros before the 8. 0.000008 4516. I'm going to stop at 4516. X cubed like that. So it's an 8 that had the decimal here, and then it said that to the negative 6 power. So 1, 2, 3, 4, 5, 6 right there. It's going to move me over there. So that's the answer. So we could substitute centimeters and get kilograms. Part B. Graph the original function and the function from part A in the same coordinate plane. What type of transformation can you apply to this to produce the graph from part A? Well, you have to multiply by the... Well, okay. All right, let's see. We're going to have 0.000304 x cubed as the first one. And the other one, a little rounded, but 0.0000084516 x cubed. All right, I really got to shrink in 0 to, I don't know how many, let's go 0 to 10. And then really got to shrink it on these y's. Let's just go 0 to 1 and see what's going on. I don't know if anything will show up, but because it's cubic, it might. Oh, it kind of showed up. Well, the other one? The other one doesn't even show up. So let's shrink that. Let's shrink it to like 0.4. That's better for that one. Okay, let's stretch out x. We can get more centimeters on this guy. Let's get about 25 on that guy. And now I need to bring y back up. Probably beyond 1. Let's say 10 again. I think I needed to expand x, not shrink y. I think that was my problem. I'm still having still suffering the same fate here. Expand x. Sorry, I'm just playing with it. Yeah, now it's really going to shoot up. At least, well, you know what? I probably needed to shoot up. I need to see this other one. Yeah, that one's significantly smaller in comparison, right? So I really need one to shoot up to see the other. But, whoopsie. In order to really see that other one take hold, though, and I don't know, this is centimeters. I guess a trout can be, I guess it can go more. Let's go to like 100 and stuff. The other one, like I said, will shoot up in comparison. But I really got to see the effect of the other cubic. I really got to see the other one shoot up as well. There it goes. Okay. So you see both of them, but one is significantly smaller than the other as far as stuff goes. Graph them on the same coordinate plane. Oh, man. I didn't get to that part. Look. One is like that, and one is like that. You know what I mean? What type of transformation can you apply to produce the graph? So you have to... I have to multiply by this. I have to multiply by that. And there's a rounded value, but you have to vertically compress. You have to vertically compress by a factor of 0.394 cubed over 2.2, right? That's what we multiplied to get there. So let me see if there's a clean version of that number. Probably not. 0.394 cubed alone is, oh, maybe. Numbers not great. I say or about the stretch factor can be, or compression factor, 0.27, 0.278, 0.13564, right? It's not great, but, you know, you're dividing almost by 50, nearly. 45, 50, something like that. So that's my answer to that. I'm kind of at the tail end of things, guys. We went a little while. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. That was the beginning part of graphs. We're now probably not going to be doing graphs for the next 5-6 sections or something like that. A lot of algebra stuff before we get back to graphs again on transforming them. We'll be graphing these again in a different light, less on tables, more on this kind of sketchy stuff, but we got to come up with intercepts and stuff. It'll be fun. We got to practice things until then. So, guys, thank you. Take care. I'll see you in the next one.